So good morning, everyone. Welcome everybody come to our Mobile Intelligent Photography and Imaging workshop. Now let's welcome our Professor Chen Loy to give us an opening.
Okay, hope you can hear me. So good morning, everyone. I'm Chen Loy from Nanyang Technological University. And thank you all for joining us at the third Mipi workshop at CVPR 2024. Whether you are here or with us physically or participating online, we are happy to have you. And first, I would like to apologize for not being able to join you all in Seattle in person. I deeply regret not being there, but I'm with you in spirit and I'm very excited for the day ahead. I would like to take the moment, next please. Yeah, I would like to take the moment to introduce other organizers who have worked to bring this event to life. Their dedications and hard work are the backbone of this workshop. So we have Xiaoming and Zhongsheng who are leading the organization of the workshop. And we have Chongyi, Shangchen, Ruicheng, Yue Kun, Pei Qing, and me, myself. We are all from Nanyang Technological University. And we also have Chunle, Xinjing from Nankai, Yachi from SenseTime, Jimmy from SenseTime, also Dafeng from Samsung Research China. So your efforts are deeply appreciated, and this event wouldn't be possible without you. Next, please. And this is the third edition of the Mipi workshop. For those who may be new, Mipi stands for Mobile Intelligent Photography and Imaging. And our workshop aims to address the latest advancements and challenges in the field of computational photography and imaging. And while the topic might not be at the forefront of every conversation these days, but it remains a critical area of research with significant implications for both academic and industrial applications. And as in previous years, next please. We have organized several challenge tracks to push the boundaries of what we can achieve. And this year we have 3 exciting tracks. I'll talk about it later. And I'm proud to have announced that we received a total of 28 submissions for the challenges. And additionally, we have accepted 6 workshop papers. And it's good to see that the community continues to grow and produce outstanding work. Next, please. And we are also honored to have 4 distinguished keynote speakers with us today. Prof. Lei Zhang from Hong Kong PolyU and Oppo Research Institute, Dr. Mahmoud Afifi from Google, and Dr. Jen Wang from Snap Research, and Men Wei from University of Toronto. And I believe the insights and expertise will inspire and enlighten us all. And next, so before we move on to our keynote, I would like to announce the winners of this year's challenge tracks. So we have 3 tracks altogether: raw image denoising, the mosaic for hybrid EVS camera, and nighttime flare removal. So under the tracks of nighttime flare removal, we have Xiaomi from China as the champion, Tianjin University as the runner-up, and Computer Vision Lab from University of Wolfsburg, Germany as the second runner-up. Next. So under field shot raw image denoising, under this track we have again, we have Xiaomi China, the camera department, to get the champion, and Samsung Research China from Beijing, together with Samsung Electronics, Sun Yat-sen University get the runner-up, and the place goes to Harbin Institute of Technology, and also the Smart City Research Institute of China, and Electronics Technology Group Corporation. And for the final tracks, the mosaic for hybrid EVS camera, we have University of Science and Technology of China with the champion. Xiaomi got the runner-up, and HIT Shenzhen IMEC, Eugene, and Northwestern Polytechnical University got the second runner-up. And congrats to all the winners. So we will present the certificate for those who are here right after the workshop, and for those who can't attend the workshop, we will mail the prize and certificate to you. Thank you all, and congratulations to all the winners. Okay, now it's my great pleasure to introduce our first keynote speaker, Professor Zhang Lei. Now, Professor Zhang is a professor at the Hong Kong Polytechnic University and a prominent researcher in the field of computational photography and low-level vision, and has significantly shaped our field and is currently with Opal Research Institute, where it is dedicated to transferring the latest AI techniques to mobile photography products. And Prof. Zhang is a senior associate editor of TIP and has held editorial positions with several other prestigious journals. And today, Prof. Zhang will be giving his talk online and will share with us his insight on how far are we from the restore any image model. Please join me in welcoming Prof. Zhang Lei.
Thank you very much, Kevin. So let me share my screen first. Can you hear me, Kevin?
Yep, very clear.
Okay. So the talk today is about how far are we from the restore any image model, because we have so many large models such as recognize anything model, segment anything model. So can we have a model which has very strong generalization capability to restore any image, okay, with different conditions? So this is, I think, for many researchers in low-level vision, this is one of our dreams. Okay, so let's first have a brief review of the development of image resolution and enhancement. So in a very early time, so we have many different very simple filters to remove the noise, such as the low-pass filter, the Gaussian smoothing filter, the media filter, and the mean filters. So with those filters, we can remove some very simple kind of noise, such as Gaussian noise. Of course, we can also use some bicubic interpolator and bilinear interpolator to improve the resolution of images. So later on, we have better solutions. We can first transform the image into some sparse domain, such as wavelet transform. Okay, so we can have some sparsity representation of the images. So in the transform domain, we can better separate the noise with signals. Okay, of course, more than 10 years ago, one very popular method for image resolution is the so-called sparse representation or sparse coding, as well as dictionary learning. So we can learn a dictionary from images so that any given image patch can be sparsely represented by the dictionary. So the performance for image resolution won't be better than those mathematically designed transforms, such as Fourier transform and wavelet transform. Of course, we also have low rank analysis. So we can collect many similar patches, put them into a matrix, and apply the low rank analysis decomposition to reconstruct the clean, bad quality image patches. So meanwhile, we have many simple functions to enhance the color of the image, such as the gamma correction, histogram matching. So all those methods, the so-called handcrafted methods, because it relies on the human price, the understanding of the image properties. So later on, with the development of image of deep learning, okay, sorry. So we have many data-driven methods by train deep neural networks. So the earlier work, including the SRCN, the VDSR, as well as DNCN. So we train a convolutional neural network to map the given input image to a better quality image to remove noise or improve the resolution. So of course, from CNN, later we have a new architecture that is the popular transformer architecture. So with the attention mechanism, the transformer can better learn the dependency among image pixels. So we have a much better resolution performance. Of course, the cost is okay. The transformer, the complexity, somewhat okay higher than CNN. So another line of research later will be the so-called real-world image resolution, or the photorealistic image resolution. So originally we use GAN. We use GAN to train a network using the GAN laws, the generative adversarial network training to enhance the perceived quality of the image. But at the same time, mostly we will lose some fidelity. So the PSNR, the SSM, those index will not be much higher, but the perceived quality will be much enhanced. So along this line, in recent years, we have new frameworks. So from the GAN network, we can have normalized flow as well as the recently developed diffusion models. So with the pre-trained, large-scale text-to-image, we can apply them to the downstream task, including image resolution. So overall, so we can see that for image resolution and enhancement, the roadmap will be from simplified tasks such as remove Gaussian noise, interpolate the image size, to real-world problems. That is, the degradation will be much more complex than simply the adding Gaussian noise or downsample the size. So on the other hand, from the methodology side, so we are from the very simple manually designed methods such as low-pass filters to the recently much more advanced methods using the data to train the model. Because the recent work on real-world image resolution mostly performed under the framework of diffusion models. So I briefly introduce some recent works along this line. So generally speaking, for the image resolution, mostly the real-world or photorealistic image restoration, those methods based on the diffusion models can be partitioned into three groups. So the first group will be the so-called decomposition-based methods. So for those methods, usually we assume the degradation process is already known, so it can be written linearly as some matrix, such as A. So those methods mostly will decompose the degradation matrix into some space, such as null space, then perform the diffusion process to reconstruct the original image. So the advantage of those methods will be they are training free, very simple. You do not need to train the diffusion model again. However, the limitations will be you have to know or predefine the degradation process. So the degradation will be known and should be linear. So for nonlinear and all no degradation, so those methods will not work. So the second line of research will be we train a diffusion model, but not for image generation, but for image resolution. So one of the representative work will be the redshift. So we can train a model specifically designed for image resolution using residual learning. But because residual learning will be very efficient, you only need to train a model to approximate the residual, but not the original signal. So the training process, learning process will be efficient. However, for those models, the limitation will be the pri. Usually learn pri is, the model is small, so the pri is limited. And the generalization performance is not very good. When we apply those models to the real world, real images, degraded images, so the result will not be very good. So the last category will be the those methods leverage the pre-trained text-to-image model. So Of course, the advantage will be the price will be very strong because new models already trained on billions of images. Okay, so the scale will be large, so the price will be very strong, and the generalization performance usually much better than previous two kind of methods. So the disadvantage is also very clear because the model is so big, so the cost will be big. The inference speed will be slow, and the controllability is not very good. So sometimes the model will give you the result you are not expected, unexpected result. So this figure shows roughly the roadmap of those methods, basically from 2020, from the DTPM. Okay, we have okay, the those works developed such as the DDNM, DDRM, decomposition-based methods. We have Redshift based on the diffusion on residual domain, as well as those recent works leverage the pre-trained text-to-image models. I briefly introduce some representative work along the last line of research, which leverage the pre-trained T2I models. So the first work will be the well-known, the stable SR. Okay, actually it's done by the group of Kevin. So this work is the first one which leverage the T2I model for image super resolution. So I think it demonstrates that we can apply those T2I models to the downstream task of image resolution. The framework actually very simple, based on the control net. The result actually at that time is very impressive. I believe most of the researchers along this line know that the result compared with those previous works on real-world image super resolution is very impressive. However, this work actually does not consider the image degradation model. So sometimes the performance is not very stable, and the high-level text information, semantic information is not exploited. And it goes to 200 steps for the diffusion. So the inference time is also very long. So later, another representative work is the PSD. So in this work, the authors designed the so-called PACA, the pixel-aware cross-attention mechanism to control the image resolution process. At the same time, those high-level information, including the text, the class information using ResNet, okay, the detection information using YOLO, and also some high-level information using BLIP will be exploited to stimulate the generative capability of the stable diffusion model. So during the inference process, so-called adjustable noise schedule is also proposed to better control the inference information, the leverage the noise, the random noise, as well as the input low-quality image together. So the disadvantage of this method is the semantic information is very sensitive to the degradation because those models are not fine-tuned. So later on, the CSR published in CVPR this year. So this work actually improved the PSD. So in the first step, the authors fine-tuned REM model, recognized entity model. Okay, by fine-tuning this model, so the input low-quality image, okay, the text information can be better extracted from the low-quality image. So then this fine-tuned model, the so-called DAPE, will be used to control the image resolution process. So the performance is much better than and more stable than the previous PSD. Okay, another recent work is the super IR. So this method scale up. Okay, so first of all, it used the SDXL, a large model, a generative model, Also, it used the LLama to extract the text description from the image. So the total size of the model is very big, and so this is the inference time is very low. And I believe one major issue is the controllability is very poor because many times, sometimes the result will be very, very good, but sometimes the result is very bad because the text information is not unstable. Okay, so those are some recent works along the line of leveraging the generative price for image resolution. So, but anyway, for image resolution, I think many works in academic research, there is some kind of gap between the academic research and the real world industry application. So I briefly summarize some difference. The first difference I think is on the data. So in academic research, usually we simulate data. We construct the training pairs to train our model. So in this process, we usually assume some kind of distribution of noise, such as the Gaussian Poisson noise for real-world images. And we also use simple operators, such as bicubic operator to downsample the resolution of the image. We can use Gaussian kernel or to blur the image. We add some simple motions. So we can simulate some degraded images to construct the training pairs. Okay, the low quality image, the high quality image. So although we already developed many different methods to perform such kind of simulation, but anyway, the real world data, they are much more complex. First of all, the noise, they are non-IID, they are not Gaussian, they are not Gaussian Poisson. They're very complex under different conditions, different illumination, different ISO. Okay, so the blur is also very complex, cannot be modeled by the simple motion blur or the Gaussian blur. So the illumination condition different, then the degradation will be different. So I show you one example here. So this image is collected under low light condition. So actually, you can see for those Chinese characters, the highlight, okay, degradation. So this is very difficult to process. So the gap between the depth between the data in academic research and real world industrial application hinders the application of a lot of methods to real world scenarios. So another a very big gap, the difference is the objectives. So for those academia researchers, including those professors, okay, PhD students, postdocs. So our goal actually, honestly speaking, most of us, we want to publish papers. So to publish papers, we have to use metrics, okay, quantitative metrics to prove that our method is better than the previous ones. So for instance, we have a higher PSNR, we have a higher SSIM index, we have lower LPS scores, so that means better quality, right? But actually, all those indexes, they cannot faithfully measure the real-world perception, the real perception of human visual systems. So I'll show you one example. So those two images. So I believe most of us will choose the second one as the better one. But for the MSE, that is PSNR, SSIM, LPS, those metrics, actually the first one, the low quality one, perceptual quality one, will have better, okay, metrics. So that means that almost all the existing metrics cannot faithfully measure the perception of human visual system. But in real world, in industry application, because I'm working at Oppo recently, okay, so I communicate with many practitioners in industry. So they mostly use different kind of incomputable objectives, okay, to measure the quality. So those objectives cannot be quantized, so they cannot be used to optimize our models. But we have to adjust our model to meet those requirements. So this process is very, very tedious. We waste a lot of time of ours. So, but anyway, I don't know how to translate those words, because in Chinese there will be something like, okay, 触摸感, 油画感, 质感, but I don't know how to exactly translate them into English. But those measures, those objectives are very hard, okay, to optimize. Okay, so let me show you some results of the representative model. When we apply those models to the real-world images, for instance, this import image is real-world low-resolution image. Okay, what will be the result? So the first two methods, they are CNN-based methods. So basically, they are blurred because the details cannot be reconstructed or restored with a better perceptual quality. So the third one and the fourth one, they are GAN-based methods. So before diffusion models, the GAN-based methods, they are the most popular one. So we can see that the first looking at them, okay, the perceptual quality will be better than the CNN-based one. But when you okay, observe those images with more time, you can see the those area, okay, the grass, the flower, actually the reconstructed output are not very natural. Okay, not very natural. So that means that they still far from the requirement in real world requirements or real world applications. Okay, the last two images, the results are from the diffusion models. So clearly, most of us know that for the diffusion models, they are very poor at those text or characters, especially for the Chinese characters. So totally wrong. This is because, first of all, the VAE, the variational autoencoder, will lose some details, and in the diffusion process, okay, for very fine scale structures, it's very hard to control. So overall, okay, the methods, those methods, the performance is still quite limited. Okay, let me show you more examples. This is another one. You can see for the diffusion models, the CSR or CVPR. So the patterns on the wall are totally different. Of course, they are also different from the original image. Okay, so because of the challenges, the real world challenges for the image resolution in the wild, in real world scenarios, and the gap between the academic researchers and industry engineers. So in this year in CVPR, we organized a challenge. We call it the RUN, Restore Any Image Model Challenge in the wild, the challenge. So the goal of this challenge is just to provide the platform, test platform for AI researchers. So this here, the AI, the A is for academia, the I is for industry. So I think this is another kind of AI. So how the researchers in the academia and the industry, so to evaluate, okay, their methods on the degraded images in the real world scenarios. Okay, we hope that this platform can facilitate the research on the RUN in the wild. So this challenge includes three phases. And in the first phase, we provide the researchers with 100 groups of images. For those images, we provide the reference GT. So we collect those images in the controlled environment, so we can have a reference GT. So we provide those GT together with the degraded images for the developers to train their models, to fine-tune their models. So meantime, we also provide 100 images without reference GT. So they are real-world degraded images, no GT, no ground truth. So in the second phase, we provide another 100 groups of paired data for them to fine-tune their models. So meantime, they can submit their result to the website, so we can provide some feedback on the result on those images without GT. So in the last phase, we invite the top 12 teams to continue the competition with another 50 groups of images. So for those images, there is no GT for them. So we evaluate the result. Totally depends on the subject evaluation. So we invite some professional photographers and engineers in this process. Okay, let me show you some example images. So this is in the first phase. Okay, those images, they are collected in real world conditions, but under controlled environment. So we can construct the pairs, the low quality image and the high quality one. The tasks actually involve those denoising, super resolution, autofocus, motion blur, and so on. So we use those full reference metrics such as PSNR SM as the metric to evaluate the result. Okay, this is the another a group of images in the second phase. So in the second phase, we provide those real-world images, okay, local images without any GT. So actually, for those images without GT, there can be some smooth details and textures, and some stroke adhesion in the super resolution process. Okay, and in the highlight area, the colors and edges can be a lot of artifacts. So for the evaluation, because no GT, so we invite some expert practitioners to subjectively evaluate the result of those competitors. So okay. So this figure shows the some challenges. You can see for this bird, actually, we lose a lot of details. Okay, for the tree, so there are some kind of color artifacts here. So for those characters, okay, the readability is very poor. For those textures such as trees, the grass, and the lake, so we lose a lot of details. So all those things, they are very important in real-world photography, especially for smartphone cameras. So we hope that the output can be enhanced with textures, details, and as well as the colors. Okay, so overall for this challenge, we received more than 200 registrations, and 39 of them submitted their result in the second phase, and with more than 400 submissions. So finally, we selected the top 12 teams to join the last phase competition. And among them, because we have a certain range of time for them to submit the result, finally we received 8 valid submissions from the 12 teams. Okay, so this is the final result for the 8 teams. You can see the top 2 teams. Okay, the top 2 teams, actually they are from industry, and all the rest 6 teams, they're from university. So, and the first 2 teams, actually the first 3 the teams, their final score are much higher than the rest. So we believe that this result actually reflect the fact that for the industry developers or researchers, they know better, okay, the requirement, how to evaluate the quality of images, especially for those real-world images in the wild. So that's why they can achieve better scores, okay, in the competition. But anyway, there's something very intriguing facts from the result. So the first place, the winner, the champion, actually this solution is not a stable diffusion-based solution. It's a GAN-based solution. So this is very surprising. So it's very difficult for us to imagine that, okay, the best result is obtained by GAN, not by the diffusion models. So when we have a detailed look of the champion solution, you can see that this GAN is somewhat unusual because this GAN, the network is much heavier than previous ones. So it's a U-shaped model with adversarial training, and the authors actually carefully designed some kind of data synthetic strategy. That means that from the very limited amount of training data we provided, they can synthesize many data, okay, with similar degradation and quality to those to our provided data. So that's why they can train a stronger, okay, a better model. and also the combined result of the original local image with the network output. So there are some kind of balance between the details and the fidelity. So this is the solution for the second runner-up. This method is much more complex than the first one. So it's basically a stable diffusion-based method, but they also employ a GAN model as a backup. That means that for some areas, okay, where the diffusion models does not work very well, okay, they will detect those artifacts and use the GAN model output to replace the diffusion-based one. So this method is very engineering, but a lot of post-processing strategies. But anyway, the final output is good. It's good, but the price, I mean, the cost is very high. So let me show you some result of the top two performers. This one is a good example. So on the left is the input, and on the right, okay, this is the first place result. This is the second place result. Okay, GAN-based method and stable diffusion-based method. You can see compared with the input, the quality of the enhanced images, no matter the GAN-based one or the SD-based one, much better than the original one, with clear details and richer details on the roof and as well as on the fence. So the perception quality is much enhanced without too much artifacts. Okay, however, so many results among the images we provide in the challenge, in the context, many images, the output, there will be some areas not very natural. So this is another example for the tree. So maybe you can see that, okay, the image, the enhanced super resolution result is much clearer and sharper than the input. But when you look at them with more detailed looking, you can see that for the leaves of the tree, actually over enhanced. So a lot of unnatural details on the leaves of the tree. So this is in industry applications, for instance, in the smartphone cameras, actually this is not acceptable. So we okay, we have to smooth a little bit for those areas. Okay, this is another example for the wall, the patterns, the stripes on the wall. You can see for the GAN-based method and the stable diffusion-based methods. So after image enhancement super resolution, actually the pattern of the wall, okay, will be much different from the original one. So both of them result different from the original image. I can tell that. And between the GAN-based method and SD-based method, their distribution results are also very different. Okay, so in this case, actually, we only see that, especially for the diffusion model-based one, okay, very unstable because the difference is very, very big. For the GAN-based one, it's somewhat we can accept it because it's natural and a little bit close to the original one. But for the diffusion-based one, deviate from the original pattern a lot. So we have more examples, especially for those Chinese characters. The output will be very bad. So you can see for the text here, no matter the numbers or the Chinese characters, okay, for the GAN-based one and the stable diffusion-based one, they are totally different from the original characters. So yeah, so actually for those images we provide in the computation, basically speaking, the quality of the input image, the quality of the low resolution, low quality image are not very, very bad. Because this is the first time we organize this challenge, we do not give the developers too hard samples to do. So we select a batch of samples with low level or medium level degradation. But in practice, we actually have many lower quality images. So those images not involved in the test, but we just test them after the computation is finished. We just test the result of the first two performance. We apply those methods to the image here. You can see the image is smoother than the previous one. After the GAN-based model and the diffusion-based model, we can see for both the Chinese characters, also the pattern, the fine-scale details in the wall. So they are very unnatural. Okay, in industry, for instance, in Oppo, okay, such kind of result will not be accepted. We have more examples, especially for the Chinese characters. The output very poor for the generative GAN-based and stable diffusion-based models. Okay, this is the low light image captured in nighttime. So the image very blurred. So after the enhancement and resolution, the output actually is far from satisfactory. Okay, so then the question is, because we only like to discuss a little bit, okay, how far are we from the RAN, the restore any image model? Because in areas such as image recognition, we have a RAN, a recognize anything model. In segmentation, we have SAM, segment anything model. So generally speaking, their performance are good, their generalization performance are not bad. But for image resolution, how far are we from such kind of RAN? So I believe we still have a long way to go. But what are the major challenges? I briefly summarize 5 points. Okay, not very complete, just for our discussion. So the first challenge is how to reduce the model complexity. Okay, for the deployment in resource-limited devices such as smartphones. So no matter the stable diffusion or other large-scale text-to-image model, precision model, actually their complexity is pretty high. So when we apply them to smartphone cameras, so including the computational cost as well as the memory, okay, actually they are very huge. So it's very difficult for us to directly implement them for image enhancement in mobile devices. So this is one of the very clear challenges. The second one is we can see from the examples I provided in the slide. So the generalization performance of GAN-based models, stable diffusion-based models, still not very high. So how to improve the generalization performance of those models for real-world, very heavy, very complex degradations? There's still one unsolved problem. Okay, the third one is how to construct fine-scale symmetric structures for very small-scale structures and textures. For instance, the Chinese characters. So using diffusion-based model, especially for those latent diffusion models, is still a very high challenge. So we lose details in the VAE process after the encoder. A lot of details removed. But recently, the Stability AI, they released the SD3, the model. So we just tested and we found that the VAE in SD3 is much better. So hopefully, we can address this issue later. But still, this is a big challenge in those diffusion models. Okay, the fourth one is how to process large-size low-quality images. So currently, the stable diffusion mostly used for image super resolution, and the input in most cases is at most 512 by 512. But in real-world smartphone imaging, the resolution of the quality, even the quality is low, but the resolution is high, is 4K. So how can we impose those high-resolution, low-quality image for the processing of diffusion models is a challenge. If we partition the large image into small patches, so the semantic information will be lost. So the output will be, I believe, we will have some problems in the output. Okay, and the last one in my list is Okay, we leverage the pre-trained text-to-image generation model for image resolution restoration tasks. But can we directly pre-train a generative model? Okay, and this model is specifically designed for image resolution purpose, not for image generation, but for just for image resolution. So I think this is a very important issue. We the researchers in low-level vision needed to think carefully, because the gap between generation and restoration is still very clear. We have a lot of difference. So although that we can use the pre-trained generative model for image resolution, but the controllability, the complexity, the cost will be very high. So if we can train a model, this model may be smaller than the T2I models, but it is well fitted, for our purpose in image restoration. Actually, we recently just in 1 month ago, we done some work along this line. Among the 5 questions, we want to address the first question first. How to reduce the model complexity. At the meantime, we want to improve the controllability of the model. So we developed this so-called OSEDIF, one-step effective diffusion model. So all those previous methods, the real-world super resolution methods, they usually they run the diffusion process for several steps. At least for maybe 3 or 4 steps, and they also needed to use the random noise as the input. So because they use the random noise as the input, they needed to run several steps to reconstruct the image, and the stability actually is not very high. So in our work, we and most of the previous methods actually they use ControlNet as the backbone, as the framework. So in our work, we do not use ControlNet. We use LoRa. So we use LoRa to fine-tune the encoder and the unit, and we do not use any random noise as input. We directly use the low-resolution image as the input. This totally remove the randomness in the image restoration process, because without the random noise, the output given the input low-quality image, the output will be deterministic without any randomness. And also, we only need to use a one-step diffusion to finish the image reconstruction process, because we believe the input low-quality image already contain enough information for the reconstruction process. So this is the training framework. So we use LoRa to fine-tune the encoder and the unit. We fix the decoder. And we use the R1 knob, the perception loss, as well as the I think the we apart from the fidelity loss, the R1 or L2, or as well as the perception loss, we also have a important loss, that is to align the distribution of the output to the pre-trained text-to-image model. So this is for the regularization of the distribution to ensure the quality of the image. And we use the VSD loss, variational score distillation, to finish this part. The paper already put on arXiv, and the code will be released very soon. I show some result. This is the performance comparison. We compare our one-step model with the previous state-of-the-art. You can see on most of the index, including SSIM, LPIPS, PSNR, CLIPS, AQA. So the one-step model is very close or even better than those previous multi-step models. But in terms of the number of parameters and the inference time, because we only run the diffusion for one step, so it's much less inference time than the previous models. And we use LoRa, we do not use ControlNet, so the trainable parameters is very small. So the result is those out on the simulated images. We can see that compared with previous methods, the one-step model is very stable because it's only without random noise at input, or only the input low quality image will be used in the resolution process. Okay, so this is another example. We compare with those stable SR, okay, CSR, and the PSD. You can see for the PSD, because it uses high-level information, if the semantic information is wrong, so the output will be totally wrong. Okay, then finally, I show the result of this one-step model in the real-world images. Okay, all those input, they are collected by our smartphone cameras in real world. So you can see for the dog, okay, the input is very blurry. And this is the result of the first place method in our competition, the RAM challenge. So this is second place method. This is the OSCD. So I believe for the hair of the dog and the face of the dog, so the OSCD works much better than those two top two methods. Okay, this is another image example. I don't know the name of this fruit, but it looks very delicious, right? So compare with those two methods, the one-step network works pretty good, okay, much better in the resolution process, very natural and with a lot of details. Okay, this is on for the building. Okay, the input image very blurry with very fine scale line structures. Okay, so the OSCD okay, restore the structures of the building very well, compare much better than the previous than those two methods. Okay, so this is the another one for the toy, very hairy the toy. So you can see the details. Okay, the hair well reconstructed. Okay, so anyway, for our method OSCD, it only improve a little bit. Okay, in my based on my understanding, we only address a little bit the first problem. Okay, reduce the model complexity. Okay, for mobile devices or other resource limited devices, and a little maybe improve a little bit the generalization performance of the model in real world degradation. But for the remaining three challenges, okay, problems, I think we still need a long way to go to do more investigation along those lines. Okay, finally, I would like to share some information. So I don't know whether you want to buy a new smartphone or not. So if you want to buy a new smartphone, I suggest that you may wait for several months. Okay, why? Because Oppo will release its next generation flagship smartphone. Okay, maybe 2 or 3 months later, we will see Oppo will release the next one, Find X8. And the very important thing is that in Find X8, our proposed method OSCD will be put inside. Okay, for 60, 100 to 100 times high quality, okay, imaging, okay, and the runtime is just in several seconds. You do not need to wait too long after you press the button. Okay, in several seconds, we will give you a very high quality, okay, image for zooming. You can use it to shoot things far from you. I believe the experience will be very different from those previous phones. Okay, so I strongly suggest that if you want to change your phone to a new one, just wait for several months. Don't be in a rush. Okay, thanks for your time. And I would like to answer any questions. If you have questions about my presentation, I will be very honored to answer questions. Okay, thank you very much.
Yes, thank you so much, Professor Zhang, for the wonderful talk on how far are we from the restore any image model. And now is the Q&A time. If you have any questions, please feel free to come up to the stage and use this mic to ask Professor Zhang directly so that he can better hear you. Is there any questions? We can also take questions from the audience online.
Yeah,
Okay.
maybe let me start first. I Professor Kevin here. So
Yeah,
I can't wait.
Kevin.
I can't wait to get the new Oppo phone. Yeah.
I can give you one for free.
Really? Okay. Just want to ask you, like, what do you think about scaling law? Yeah, how do scaling laws influence the direction of research in computational photography? And are there any risks that focusing on scaling could overshadow other important research areas?
I think the scaling law is very interesting. So I believe the scaling law has already demonstrated its practice in many other areas, such as large language models and also vision language models, as well as in image generation, such as the stability AI. They released the SD models. So all those models have already successfully proved that if we have a very large scale of data and we train a model with enough size, so the result will be very impressive. So I believe this law is correct in some sense. But for image resolution, whether the scaling law is the key factor or the most important factor, I am not very sure because so in a way, the resolution is a very different problem from recognition from generation. So we have a very different requirement. For instance, if you want to, okay, in resolution process, you cannot change the content of the image too much. Okay, of course, if you can change it, it basically becomes a generation problem. So we have to maintain the fidelity of the image. So in such kind of sense, can we collect enough data, training data, okay, on the different imaging conditions to train the model? I think this is very difficult. And the quality is another issue. So in image resolution, we have very high standard for the image output image quality, especially in industry. The engineers they check, okay, they test our algorithm every day and give us a lot of actually questions on the output, the performance. So but anyway, I believe we have to use enough data to train our model. But the amount of the data is just one factor in the whole process. We have to design better architecture. We have to pre-train a better model, maybe a pre-trained model, or the training strategy, okay, and many other issues. Especially, I believe one unsolved problem, in addition to the to the scaling law in image resolution, is the metric. Okay, how can we measure, okay, quantitatively measure the quality of the output? So this is not solved yet. So because of this, we do not have very good loss or optimization objective to optimize our model. So all those factors together make the image resolution a very complex issue. So only using the scaling law, I don't believe it. I don't believe the scaling law will address the challenges in image resolution in the wild. So we have to combine with many other techniques and ideas to address it.
Agree. Thank you.
Hello. Thank you, Dr. Zhang, for giving the talk. I'm a PhD student with Michael Brown, and Michael talks very highly of you all the time, so it's very good to hear you. And my question was, the examples that you showed, when you use like a GAN or diffusion model, you're trading off perception for distortion, and there might not be signal in some of these examples to actually reconstruct the ground truth accurately, and you might what we call, like, just kind of make up something, right? And so what do you think about that, and how are you knowing if you're trading off perception for distortion?
Oh, yes. Thanks for the question. And please say hello to Michael, okay, when you go back to Canada. So I have not seen him for a long time because of the pandemic. Okay, for your question, I think it's a very good question. This is also one of my concerns when my group, we are working on a diffusion model-based algorithm for image super resolution and other resolution tasks. So how to balance between the fidelity and the perceptual quality? I think it's a very difficult issue. So you can see from this picture, I believe most of you will, if you choose, you will choose the OSCD one, but because this output is clear, is very natural, but how is the fidelity of image? We don't know because we don't have ground truth. But suppose if we have ground truth, I believe the PSNR or the SCM index will not be very high because after the diffusion process, okay, the fidelity will be reduced a lot. So in image restoration, I mentioned okay, it's different from image generation. So fidelity is a very important factor we should consider in designing our algorithm. But the traditional methods such as those CNN-based methods or the transformer-based methods, okay, they can give us a high PSNR, but the perceptual quality is very low. So this is the trade-off between the two objectives. Do we have a solution to solve it? I think we currently do not have a very effective solution to find one output, okay, which can have both high fidelity and perceptual quality. But I don't think this is a problem cannot be solved forever, because for example, I told my students several times, suppose we have a circle. Okay, this circle is the range that for the fidelity. That means that any solution fall into this circle, okay, will satisfy our requirement for fidelity. Then how can we find the one among, okay, within this circle, how can we find the one which has the best perceptual quality? So if we can do it, okay, this is basically a searching problem, but the complexity of the searching process will be very high. But if we can find a good algorithm, okay, to search within a range of candidates, okay, those candidates can have enough fidelity, then we can find the one, okay, locate the one which has the very good, okay, perceptual quality. This can be one solution to address this trade-off. But currently, no matter we use the CN architecture or transformer or even the those stable diffusion models, we have many different loss functions such as perceptual loss, the gain loss, okay, and the L1 norm, L2 norm, or many other loss design. All those existing methods, okay, will trade-off between the fidelity and the perceptual quality. So this is unsolved issue. But I believe we should be able to address this issue in the following years. Okay, I'm actually I'm working on this issue. I have some very rough idea, but not a very clear solution yet. So I hope that all of us, okay, the researchers in image restoration should think carefully. Okay, how can we achieve enough high enough fidelity? Okay, when we pursue the perceptual quality.
Thank you.
Okay, thank you for engaging questions. And also a special thanks once again to Professor Zhang for you sharing your valuable insights with us today.
Okay, thank you very much. Okay, bye-bye.
Okay, bye. And now, let me introduce our next keynote speaker. And our next keynote speaker is Dr. Afifi. And Dr. Afifi is currently a software engineer at Google. And prior to joining Google, He worked as a machine learning and camera algorithms engineer at Apple. He earned his PhD in computer science from York University in 2021 under the supervision of Professor Michael Brown. And his doctoral research won 2 distinguished dissertation awards across Canada and a Best Paper Award at the 27th Color and Imaging Conference. Dr. Afif's research interests lie in computer vision and computational photography, with a particular focus on color-related research. And Dr. Afifi, please feel free to begin your sharing when you are ready.
Thank you for the introduction. It's a pleasure to be here, although I'm presenting remotely. So can you see my screen? Hello, can you hear me?
Yes, we can hear you.
Yes, okay, so you can see the slides right now?
Yeah, we can see right now.
Okay, thank you so much. So today I'm gonna talk about image weight balancing, and I will discuss like different aspects than the major stream of image weight balancing in academia, or like the common way we treat white balance. So I will start with in-camera auto-white balance correction, and then I will discuss camera-independent illuminant estimation. Then I will go to discussing post-capture white balance correction and editing. And then I will discuss spatial white balance correction and the impact of white balance errors in high-level computer vision tasks. So to start, we need first to like review how we perceive colors. And basically, colors is a sensation that we perceive based on 3 different components: the object spectral reflectance component, and the spectral power distribution of the illumination in the scene, and our eye sensitivity. And in the case of capturing an image, we can replace the eye sensitivity with camera spectral sensitivity. So in this case, we construct a raw image, and this raw image goes through, just one second. You still can't see my screen, right? Like the full screen presentation?
Yes, we can see you.
Yeah, thank you. So yeah, so we start from raw image. That's the first thing formed in when we take any photo, and this raw image goes through some processing to get the final sRGB image through what we call camera ISP. So camera ISP includes several components. There is no standard way of like designing camera ISP, but usually we have main components. One of them is white balance correction, and usually white balance correction coming with color transformation. So we do white balance on raw image, and then we transform the colors of raw image after white balance to one of the standard space, for example, CIE XYZ or linear sRGB. This transformation is done in a calibration based way. So we calibrate this transformation using a 3x3 matrix. And this have a lock into white balance. So white balance, usually we have a raw image like that, and our goal is to white balance the colors of this raw image. And in the case of we already have a calibration object like color chart in the scene, we can manually select any gray patch that represent the illuminant color in the scene, and the additional bias or like unwanted bias that we try to remove caused by the camera response function. This called this greenish tint in the raw image. Once we have this illuminant color determined, we can use a diagonal correction matrix, simple diagonal correction matrix that multiply all the R and G and B values in the image with a global scale factors to get the white balanced raw image. In reality, we don't have this color chart object, and we would like to do auto white balance. So we run that through an illuminant estimation algorithm that predict the illuminant color in the scene. And once we have that, we do the correction in the same way. And typically, to measure how accurate the illuminant estimator is, we use angular error. So it's a metric that measures the angle between the estimated illuminant color vector versus the ground truth one obtained from calibration object like the color chart. And we can categorize illuminant estimation into statistical methods and learning methods. So statistical methods are simple, easy to implement, but less accurate compared to learning methods. But learning methods still have some issues that we will discuss today. The very common example of the statistical methods is gray world assumption. So that assume that if we compute the average color in the raw image, that give us a roughly good estimation about the illuminant color in the scene, and we can use that to correct the image. It works very well in several scenarios, like this example, but it cannot work in tricky situations like this one, where the dominant color is not the illuminant color. So, and to gauge how bad the gray world is, doing this example, we need to see another more accurate example for this scene using, for example, DNN. So you can see the differences between colors of using gray world versus the deep neural network solution. And typically, the deep neural network solutions, like any other learning-based methods, require some training data and some ground truth. And in our case, and for illuminant estimation, we have a training raw images captured by whatever some target camera model we try to train the DNN for. And we have the illuminant color distribution, like each point represent a ground truth illuminant color for each scene in our training data. So based on this scheme, several methods have been introduced, like with different architectures, different input representation, like histogram feature, and going beyond the single image assumption, we have some papers proposed to use two different images of the same scene captured by the camera available in smartphone cameras. Some methods propose to use depth information in addition to the raw input image to predict the final global RGB of the illuminant in the scene. And we have our recent work that proposed to use long and short exposure images, raw images that are available in HDR imaging pipeline to reduce the number of parameters and achieve good accuracy. So regardless of what architecture we use, we recently see very impressive results in white balance correction and illuminant estimation using global assumption, and we can see errors below two angular error. And below two angular error usually is just noticeable difference, which means like you cannot distinguish between a white balanced image with angular error below 2 versus the ground truth one. So the question is, are we done with white balance, or we still have some direction of research that need more explanation? So one of the big limitation here in this learning-based methods is the fact that if we change the camera, we change the ground truth distribution. So for example, here I'm showing a set of scenes around 200 images captured by different cameras from NUS dataset. And I'm plotting the color distribution of the ground truth of the same exact 200 scenes. So we can see there's a big differences between the color distribution of ground truth from camera to camera. And that makes sense because we already discussed the image formation equation, where the camera's sensor response function play a major role in informing the measured color and in forming the raw color as an input as well. So once we change the camera, we change the input color meaning, and we change the ground truth. That requires to retrain any deep neural network model on any new camera. And of course, that's not practical solution at all, because that requires collecting new training data. So to solve that, we have a few attempts in academia that target to do raw-to-raw mapping, kind of domain adaptation. So we can map all images coming from the new camera to the old camera, and then do the illuminant estimation and project that back. So this kind of raw-to-raw mapping doesn't be designed to solve the illuminant estimation problem when we do cross-camera running, but it's just a general way of doing row to row. So one of the early work in this, assuming we have a color chart present in each scene. So it's kind of calibration-based method that assume we have a color chart of like present in camera A and camera B space, and then we capture that and we compute some mapping function to go from camera A color to camera B color. And more recently, we proposed a semi-supervised row-to-row mapping. So the idea is we try to use deep learning with a more practical setup. So we assume we have a data set of unpaired data set from camera A and B that we try to do the row-to-row mapping between them, and a small set of paired images from both cameras. And we do training in two different phases, like when we have a training example coming from the unpaired set, we do self-supervised reconstruction loss. And when the training example coming from the paired set, which is a very small one, we do traditional supervised loss. And at inference phase, we simply swap the decoders so we can map from camera A to B and from camera B to A. And more, and of course, this was mainly targeting the neural ISP, like the entire ISP, because in neural ISP, we train a network to map from row directly to the sRGB, and this network implicitly doing all the traditional camera ISP steps. So in this case, if we train on camera A to map from row to sRGB, and then we take this trained model and run through camera B, we will not get good results. So instead, we propose to do the mapping first to map any image from camera B back to camera A, and then run our neural ISP, and then we got the final result. So here is an example of image taken by iPhone and the final rendered image from the same device. And we in the right we have image taken by Samsung, and it rendered with ISP trained on Samsung images. And in the middle we map the raw image from iPhone to Samsung space, and then we render that through the ISP trained on Samsung ISP on Samsung data. So this was the main purpose of this kind of row to row. While in theory this may help in illuminant estimation, like the cross-camera illuminant estimation, but still we need more experiment to validate whether that will help or not. And more recently, RowFormer was presented, so it's a fully unsupervised framework to do the row-to-row mapping. But still, this way of solving the problem require to add additional computational costs before running the illuminant estimator, and again it require to be practically validated to see whether that will help the cross camera generalization for illuminant estimator or not. So instead of having a separate step to do the row-to-row mapping, and our work in BMVC 19, we tried to include this kind of sensor mapping in the framework itself. So the idea is, instead of working directly on row space to do the illuminant estimation, we learn in unsupervised way, a working space that kind of minimizing the differences between the raw images from different cameras. And then we do the illuminant estimation in that space. So it's very simple, like architecture design. We start with raw image, and then we go through a simple neural network that predict a 3x3 matrix. This 3x3 matrix multiplied by the raw image to give us the mapped image. And then we do the illuminant estimation on this mapped image. And the final predicted illuminant color is produced by multiply this predicted illumination vector by the inverse of this matrix. So we train on different cameras of the same set of scenes, and that gives us on average better results than the statistical methods, like the simple one that's sensor independent by design. and on par results to the average sensor-dependent learning methods that require to retrain for each new camera. And then we extend this, or like we propose another way to solve this problem in C5, the cross-camera convolutional color constancy in ICCV 21. And the main idea was to rely on additional images that randomly captured by the testing camera that's unseen during training to do the illuminant estimation. So we built on top of the convolutional color constancy by John Byrne and Yonta. So the convolutional color constancy is proposed to work on histogram space instead of directly process the raw image. And then we learn a filter in frequency domain, and then we add a bias and apply softmax function that give us kind of a heat map of where the most likely histogram bin that represent the illuminant color. So in C5, we propose to have an additional model generator network. So this model generator network learn to produce a filter and bias by seeing the histogram of the input image and additional histograms of additional images taken by the same testing camera. And the main idea here is this generator network will learn by seeing some examples, additional examples taken by the same testing camera, like how we can produce a better filter and bias that will fit to this particular input histogram. And by doing this, we achieved better results than our BMVC work, the SIIE, and with a less computational power. So I'm just trying to fit with time. So yeah, right now I will talk about the post-capture white balance. It's another aspect that is less explored. And the idea here is we just need to assume a scenario that's sometimes happen where the white balance correction on board the camera has some errors. So in this case, we will have incorrect white balance image here in linear space, and then we have a photo finishing that applied in the camera ISP to get the final image with this kind of reddish or bluish color cast. And we need to remember that this kind of photo finishing is not standard. There is no standard steps. It's a camera specific, and the goal is not to produce any standard color. The goal is to produce pleasing photographs. That means if we capture the same scene by different devices, we may observe different colors, and that makes the problem hard because it's not a standard like way of rendering the image, so we can undo the steps to fix any mistake in white balance during the capture time. So if we start with the image like that with a bluish color cast, and we follow the same diagonal correction matrix, and here I will assume we manually select an achromatic reference point like this one, which represents the best case ever. So that means the illuminant estimation is 100% accurate. And we do the diagonal correction, we will get this result compared with if we do the white balance correction in a proper way on board the camera during the capturing time. So you can see the difference between the diagonal correction in post-capture time versus the diagonal correction with accurate white balance on the capturing time. So the goal is how we can go directly from here to here in case we face an image with white balance errors. And we start with replacing the diagonal correction matrix. So instead of using the diagonal correction matrix, we propose to use a polynomial mapping function M that maps the RGB colors of the input image after projecting them to polynomial space to the ground truth. So if we do that, here I'm assuming we have access to the ground truth as RGB, which is not the case. But if we do that, we can get much better reconstruction compared with the diagonal correction. So how we can predict the matrix M? So we propose in CVPR19 a data-driven solution. We start with a data set construction. We begin with raw images and we render them through a software camera ISP that mimic the actual camera ISP, and render the same image with different white balance corrections. So that gives us different versions of images of the same scene with white balance mistakes. And then we manually select the achromatic patch so we can get the ground truth in its RGB space. And by doing that over and over through many raw images, we construct 65,000 images, and that's our training data. Then we built a simple framework that for each pair of images, we compute the matrix M, and then we represent each input image here, like for example, this one, by a histogram that's later projected to a very low dimensional space, around 65 by PCA. And then we stored the feature V here with the matrix M as our training, like as our model. So our model is around 20 megabyte, is reasonably small. And in testing time, we get an image. We don't know anything about the camera pipeline of it. We don't know anything about the white balance. And then we go through a simple steps, compute histogram, then compute the PCA feature, look into the nearest examples in our training data, and then interpolate between the pre-computed matrices to correct this image. So by doing that with a very simple framework, we got much better results compared with commercial options like Photoshop, auto correction, or auto tone, and compared with the diagonal white balance correction by using the exact reference point from the color chart, which is represent the best solution using the diagonal correction matrix. So here I'm showing examples like input image and Photoshop correction and diagonal correction, and our result versus the ground truth. We used to have an online demo and by scanning this QR code. I hope you can hide this. So by scanning this QR code, you can check the GitHub page. I'm not sure if the demo is still running, but we used to have this demo. So you can upload your image and see the image corrected. So of course we can replace the entire handcrafted design we made by a single neural network. That's of course can be implemented using an unit, for example, like this. But we can basically do more by not just only doing the correction. We can do white balance editing to match any user preferences. So here, instead of training with a single decoder, we have different decoders, each dedicated to a specific white balance task, either auto white balance correction or rendering the input image to one of predefined white balance settings. And at inference time, so we downsample the image, go through the network, and then we compute the polynomial fitting, and then apply this fitting, this polynomial coefficient to the high resolution image. That makes the framework stable and like can work with high resolution images without any computational resource problems. And then, of course, at inference time, we can switch between the decoders based on the task. So if we would like to do auto white balance correction, we can use the decoder that trained on the ground truth of patches with accurate ground truth correction. If we would like to produce shade white balance rendering, we can use the decoder that trained on shade white balance, etc. So here's an example of the input image versus the auto white balance correction and indoor white balance correction and outdoor white balance correction. And since we used two different extreme white balance presets, the indoor one and the outdoor one with two different CCT values. So if the user prefers to produce something in between, we can interpolate between the two output images from those decoders. So here I'm showing an input image examples and our k-nearest neighbor framework that in CVPR19 versus the deep white balance editing. Here I'm showing an example of comparing our result here versus photo editing software in smartphones like Samsung and Google Photos and iPhone. At the time, it was not that old. And you can see the deep wide balance correction achieved much better results compared with others. And by scanning this QR code, you can check our code, and we have a nice GUI, so you can load an image and do the auto white balance correction, or you can choose to select what the target color temperature you would like to render the image. And keep in mind all of that in post capture time, so there is no need to access the raw image to achieve these results. So after this work, we few attempts were proposed, achieving promising results using different loss function, different way of instead of using the polynomial function, they use lookup table, for example. But then we start focus more on doing white balance editing in post capture. So not just only the correction. Let's try to get the white balance editing more accurate in post capture time. So and the idea is very simple in this work in CIC 19. So this is the traditional camera ISP. We start with raw image. We render the final sRGB image with some white balance settings. So what we propose is to take a subsample, a very small representation of the raw image, and render that through the same ISP pipeline with the different white balance settings, like with the different CCT values. And that will give us different small versions of the same image rendered, and we compute a subsample of the final rendered image that's shown to the user, and we compute the polynomial mapping function between the subsample image and the produced output from this thumbnail image with different preset white balance settings. Once we have this mapping coefficient, we can store that as an external metadata in the JPEG file that doesn't require more than 6 kilobytes. And at inference time, if the user prefers to change the white balance settings, we can load up the corresponding polynomial mapping function and blend between the nearest key points based on the selected color temperature by the user. So it's a straightforward but very efficient to have the post white balance correction applied in after capture. And another work, maybe I just want to speed up, was trying to include the improve the way of interactivity with the user. So instead of determine the color temperature, how about similar to Lightroom, we would like to manually select a reference point from the scene and see the image corrected with that in a better way than the diagonal correction. So for this example, there is no single answer that can solve this example, because it's a mixed illumination scene. We have two different lighting conditions. So if we take an example, a reference point from here and here, and try to fix the image based on that using the diagonal correction, we will get this results. But if we do better mapping, we can get much better results like this. So how we do that? We use the same polynomial mapping, but instead of trying to predict that directly, we need to link the polynomial correction with anything that's easy for the user to select from the scene, right? To improve the interactivity. So the user can select any color from the scene, and that will be represented as RGB. And we would like to have a link between whatever selected by the user and the proper polynomial correction that can be applied to this example. So again, it's a very straightforward framework. We have our training data, and then we compute the polynomial between each pair of images, and we compute the average color that represent not the average color, actually. We run an illuminant estimator to predict the illuminant color in this scene. So we have each example in the training data represented by the RGB color, represents the dominant color in the scene, and the polynomial fitting matrix. Then we cluster our training data, and then for each cluster, we compute what we call the rectification function, rectification matrix. So the rectification matrix try to make this link between the RGB vector and the higher polynomial coefficient that can fix this image. And at testing phase, we take the image and then we either run auto illuminant estimator in sRGB space, or we let the user to select the reference point that the user would like to do the correction for, and then we find the nearest cluster, apply the rectification matrix to the RGB of the selected vector, and then we do the correction. And here I'm showing a comparison with Lightroom. So for Lightroom, we can manually select a reference point to fix the image, versus our result here. We can select the same reference point and get way better comparison results compared with the Lightroom. I think this is like very fast. I will recap about the spatial white balance correction effort. So for now, all the effort done was focusing on the global white balance correction, with the assumption that we only have a single illumination color in the scene. But in reality, this condition is not always the case. We have many scenes with multi illuminations, right? So in this particular example, we can see we have indoor light here and outdoor light here. So if the camera correct the white balance for the outdoor light, we will get incorrect white balance in this region. And if we try to fix for this region, we will get a bluish color cast from the wrong white balance correction in this region. So how we can do both or more than two illumination. So this is the work presented in WAGV 2022. And the main idea is we propose to replace the entire illuminant estimation step in traditional auto white balance inside the camera ISP. And instead of doing the illuminant estimation, then diagonal correction, we propose to render the same raw image with different white balance presets that's fixed. And then we have a neural network that learn how we can spatially blend between those images together to get the final image. Of course, we process in low resolution, and then we do post-processing to apply to generate the final weighting maps in high resolution image. So the main hypothesis is that we can actually blend between different colors produced by different white balance settings linearly to generate the final white balance corrected patch. And the network, by seeing different, the same scene rendered by different white balance corrections, the network can understand or can learn how to select which patch most likely is representing or close to the corrected white balance settings. So we train on patches from our training data, CVPR19, and since the entire DNN is convolutional neural network, so we can do spatial correction. So here's an example of the image rendered by different white balance settings and the output from the DSLR camera versus our output here by learning how to blend between those three images. Of course, to do some quantitative evaluation, we have a synthetic data set rendered from graphics, 3ds Max, with different white balance settings and ground truth. Here I'm showing some examples of a mixed illumination correction versus the camera output. So you can see the bluish cast from the incorrect white balance versus our results here. And the same, you can see there is a bluish tint here, a bluish cast in the person from the shaded, because it's an under shaded region compared with the other part in the scene versus our results. After that, there is based on the idea of blending between presets or like a finite set of white balance settings. Recent work in CVPR24 proposed to use a style, like to treat the problem as a style transfer, or in this CVPR, there is a recent work proposed to predict the illumination first and then learn the weighting map. And of course, I will just go very fast here. Like all the presentation talk about the image quality, but how about the impact of different computer vision tasks like image classification or semantic segmentation? Basically, this work did a study on showing that if we have incorrect white balance settings in the testing images, that can impact the accuracy of image classification and the semantic segmentation. And we observe around a 10% drop in image classification accuracy on ImageNet. And that affected the attention of different layers in trained network. By adding more aggressive white balance mistakes in the image, we can fool most of the common architecture for image classification. And to solve that, we propose a data augmentation way based on the white balance instead of using the unrealistic traditional color augmentation like color swapping or RGB jittering. So instead, we propose to use a more realistic white balance augmentation, and that was shown to improve the results and making any trained network on this kind of augmentation more robust against different white balance settings in testing images. So for example, you can see here the results without augmentation versus the result with augmentation for semantic segmentation. And here I'm showing some mistakes by model trained on CVPR10. When the image got different white balance settings, you can see the networks start to predict wrong classes compared with when the white balance was properly applied. That also helped to do scene relighting and the illumination estimation challenge in M2020. And of course, this work was done with amazing researcher. Thanks for them. And in summary, I try to answer this question, and I hope after this talk, it's clear that the answer is big no. We still have much to explore in white balance. We haven't done enough effort to do a learning-based camera-independent white balance accurately. We don't have a lot of effort done to explore spatial and temporal AWB or post-capture white balance correction or the impact of white balance on different computer vision tasks. And thank you for attending, and happy to have your questions. Thank you.
Yeah. Thank you so much, Dr. Afifi, for the exciting talk on revisiting image white balancing. And now it's the Q&A time. If you have any questions, please feel free to come up to use this mic to ask Dr. Afifi so that he can better hear you. Any questions? Okay, please.
Thanks for the nice talk. I have a question regarding the post-capture white balance correction. So as we know in the timeline pipeline, the white balance correction is applied in the XYZ or we call linear RGB space. But other than that, we still have many other post-processing like saturation or tone curving. Some of them non-linear. For those, and they may be different for different cameras. You also mentioned that, yes. So when you're creating the data set for learning-based approach, have we considered the impact of this different impact from different cameras? Where you have any domain gap if you want to apply it to some camera that does not reflect it in your data set? Will this cause some issues?
Thank you for the question. It's a good point. Basically, we tried our best to consider diversity in our training data. So we render the same image with a different picture style in the software ISP we used. that represent kind of different way of photo finishing steps. But of course, it will not cover everything. So the idea here is, as we add more diversity in the training data, we create kind of meta camera that represent a general representation of the cameras. But if there is something completely different or out of the training data, of course, that will not be handled by any method trained on this data set. Yes.
Okay, thank you.
Okay, once again, thanks, Dr. Afifi, for sharing your valuable insights with us today.
Thank you.
Okay, thank you.
Thank you.
And now let me introduce our next keynote speaker, Dr. Jian Wang. And Dr. Wang is currently a staff research scientist at SNAP. He's leading the SNAP Research Computational Imaging and Photography team. He earned his PhD from Carnegie Mellon University, and his research interest mainly lies in computational photography and computational imaging. And Dr. Wang, please feel free to begin your sharing. We are ready.
Hi, everyone. My name is Jie Wang. Thanks for coming and listening to my talk. Today, I'm going to introduce a series of our work about towards a better camera in the mobile app and AR glass. This is our team. So I'm a research scientist. Sizhuo is also with us. Sizhuo, can you raise your hand? Yeah. Okay. So we have Bing and Chuan, and we also have Andrea as our program manager and Anne as our software engineer. So in the past, Shri Nair founded this lab, and we also have Mohit and Changxi as our consultant professors, and Guru as our very senior research engineer, Carl as our mechanical engineer, Michael as our electrical engineer. So our background is quite diverse, and then we work together to work on some very fancy projects. So this is our lab. So our lab is located in New York City. Actually, it's in the center of New York City, very close to Times Square. And this is the inside of our lab. So our lab has a pretty big space. So every year we host many interns. So this year we have 8 summer interns. Okay, so maybe I should firstly introduce what is Snap and what is Snap doing. So Snap's main product is the app. It's a multimedia instant messaging app. It is widely used in North America and other countries. It is very close to WeChat actually. It has 5 tabs. So in the center, yeah, okay, you guys can see my mouse, right? Yeah. So if you open the app, then you will see this camera interface. So you can quickly capture image, and then in the left is the messaging tab. So here are your friend list, and then the leftmost is the map. So if you swipe to this tab, you can see where your friends are, and then for the first tab here is you can see the stories of your friends. So you can see what your friends are up to, and then the 5th tab is the short form video. So you can enjoy a lot of user generated videos. So this one is like TikTok. And Snapchat is quite popular. So it has 422 million daily active users as reported in Q1 2024. Another product from Snapchat is the AR glass. So it is called Snap Spectacles. It is an industry leading AR glass. Okay, So with these two core products in mind, like one is the app, mobile app, and the other one is the AR glass. And then we did quite a lot of research projects around these two. So for the app, we have two themes. One is towards a higher quality camera. Basically, it's image restoration. Okay, and then second one is a more interesting camera to make the make your selfie image more interesting, more funny. And actually, Snapchat is the first company to deliver this. Basically, it's image editing manipulation. And okay, so for the left two parts, so they are pure software based. Then we call it a computational photography. And then for the AR glass, we did two themes. Okay, we did a project of two themes. One is a better 2D camera, and okay, a better 2D camera hardware and a better 3D sensor hardware. So since this is a co-design of hardware and software, we call it computational imaging. Okay, so first one, so why do we focus a lot on quality, on improving the image and the video quality? Okay, so well, this is the data from TikTok, but we also have our own data. But unfortunately, I cannot show it here. But the results are the same. Okay, so the first plot shows the video quality statistics in the platform. So you can see that actually most of the videos quality is in the middle range. Okay, and then TikTok found that, we also found that. And the average watch time is positively correlated to video quality. Okay, so well, this social media company, we wanted to. So the most important thing is well, make money, and then second important thing is to increase the engagement of the users. So this product shows the importance of quality, of improving quality. Okay, so we did a series of projects around quality. So for example, first quality assessment. Okay, so we have so we did like a face image quality assessment, video quality assessment, container level quality, video quality assessment. Well, so basically container level means like to judge, to predict whether this video is interesting or not. And the second one, video quality. So this is just a pixel level quality. And the second one is a face restoration. Okay, so face actually a majority of the images in the Snapchat platform is face. Well, people like to take selfies and share with their friends, right? Okay, so for them, face restoration is quite important. So we did several like a fast face restoration, which could be used in the mobile phone, and a single reference based. So adding additional reference image to help the face restoration, and then multiple references. Okay, and then human body, and then for and the next one is a scene restoration. So we have like a low light, so we need to solve this problem, like low light, low dynamic range, low quality, under display camera, and then QR code. Yeah, QR code is a very important thing. So well, people use a QR code to scan many things every day. And then segmentation. So we have like robust sum, which will appear in this year's CVPR as a highlight paper, and then robust matching. So and then this matching will be presented in SyncGraph this year. Okay. And then actually this thumbnail shows the result of our robust sum, robust segment anything on low quality images. And then lastly, we did we also did projects around improving the video quality. So we have video frame interpolation and a video super resolution. Okay, and then I'm not going to cover everything. So I'm going to introduce some of them. First, face restoration, and then quality assessment, and then QR code. Yeah, okay, how to scan the QR code from a very long distance, and then video frame interpolation. Okay, so first and foremost, okay, very important thing. So we need to improve the face image quality, and we have 3 projects. Okay, so the first one, the leftmost one is just a blind portrait enhancement. So the input is just a low quality image. Okay, the goal is this image, and then second one is adding a single reference, right? And then we also have a variation that we have multiple references. Okay. Okay, so let's look at the first one, blind portrait enhancement. By the way, so this feature has been shipped. Okay, so this is what the UI looks like. So after the user capture image, then the user can tap enhance on, and then the noise will be removed, and all the blur will be removed. Well, sorry, I will not cover the specific tech here because it's in the product, but I would like to introduce what kind of challenges that we have solved. Okay, first one, so we are working in sRGB domain, not a RAW domain. So this is very different from Oppo and Google. So they can get a raw data, but we cannot. And we do not. We sometimes can get a raw data, but we do not like raw data because you know our app is running on many different kind of like iPhone and Android phones. Then it's better that we have just one algorithm for every phone. Yeah, and then for some Android phones we cannot get the raw data. Yeah, so then it's going to be. So if we customize one model for one specific phone, it's going to be a headache. Okay, yeah. So yeah, we work on sRGB domain. Okay. Second one, real complicated declarations. Well, because you know, all this raw data have gone through many different kind of ISPs, right? So then yeah, very complicated declarations. And then third one, very fast. Okay, our users are not patient. Okay, it cannot wait your algorithm to run for like 1 second and give them the result. Our users only want to wait for like 100 milliseconds. Okay. By the way, and then since I talk here, so then I can mention that the other big difference between computational photography in Oppo and Google and computational photography in an app like us. So for example, night mode, right? So well, in the phone manufacturers, the goal is to make the native camera very close to a professional camera. Okay, but our goal is just to increase the engagement. Okay, so we want the user to capture more, and they send more. Okay, and then one example, night mode. Okay, so iPhone, Google have this night mode that wants the user, so needs the user to hold their phone for like 1 to 5 seconds to capture the burst of frames and then combine all of them. But our users are not patient. Okay, they cannot wait for like 3 seconds, right? So that method does not work here. So we always start from a very bad data. So just one single image, expert time less than like 30 milliseconds. Yeah. Okay. And next one, restoration versus generation. I think if you work on face image restoration, you will know, right? So you do not want, so users do not like the output does not look like them, right? So the identity should not change. Okay. Well, so actually, so if you change the identity a little bit, right, they can easily identify that, right? Then they will feel that, oh, your app sucks. Okay, I don't want to use it. Okay, and then and then for this restoration with generation, okay, if your algorithm is not good, you change the identity a little bit, then the better way is that you do not ship it. Okay, and then inclusive. So so our algorithm should work for different skin tones, right? This is very important. If we do not deal with this issue well, then people will complain that, whoa, why? So this camera is racist. This is a very serious thing. Lastly, natural output. So the result should not be over smooth. Okay. Okay. So I just talk about the blind face restoration. Okay. So blind face restoration. So the input is just one bad image. Okay. But one degraded image does not have enough information to get the output, especially some like very detailed, especially some facial details. Okay, at this moment, then it's better that we have a reference image to help. So this reference image is captured at another time at a better condition. Okay. So this is so it has also been shipped. So this is the product UI. So the user can select the reference image. So this reference image is from your album. Okay, and then so our method. So yeah, so for face restoration, broadly speaking, there are two categories. One is non-reference based face restoration. I see so here is like a dual face. Okay, I see many authors sitting here. And then reference based face image restoration, and I think SFFnet DMDNet is by Xiaomi, right? Yeah, yeah, very good papers. And then this is our paper. So our paper. So yeah, this is our method. So we can achieve high quality as well as high identity preservation. Okay, so how can we do that? So we have to think about this problem, reference-based face image restoration. Okay, so think about one problem. Okay, so if there is a mole in the reference image, but no mole in the ground truth, what should the output look like? Yeah, Okay, Xiaoming, what do you think? Yeah, so the reference image and the ground truth could be different because you know because of different makeups, right? Yeah. I'm also not sure. Yeah. Okay. Yeah. Okay. So people actually in their loss design, they always use L2 loss between the output and the ground truth. Basically, they wanted the result to restore back to the ground truth, right? But we argue that this is not the right thing. So we think that okay, to answer this question, okay, if there is a mole in the reference image, the output should also have a mole, okay, as long as it does not have a conflict with the input. Okay, meaning so the output. So if the input is not that bad, and you can clearly see that there's no mole, then the output shouldn't have a mole. But if you cannot see whether there's a mole in the input and the reference has a mole, then the output should also have a mole. Okay, so okay, to summarize, so we set a new goal, okay, based on what I just said. So we should copy features from the reference image as much as possible, and output should be semantically consistent with the degraded input. Okay, and then face should be realistic and generate the details. Well, yeah. Okay, and then to realize the new goal, we come up with this new combination of loss. Okay, so remember that we should do two things: copy features from the reference image as much as possible, and then okay, and then output semantically consistent with the degraded input. Then we propose to use special minimum loss. So the output should be either very close to the reference or to the ground truth. Okay, and the output as a degraded version should be very similar to the input. This is cycle consistency loss. Okay, and then we also add the other two losses like identity loss, adversary loss, which are common. Okay, and then let's see the result. So, well, this is our co-founder, Bobby. Okay, so we found old news about him, and then we crop his face here. Okay, and then if we apply non-reference or traditional like a GFP GAN, this is the result. Well, the result this image looks beautiful, right? Very high quality. Okay, and so this is our result. So the difference is what? The difference is, so you can see that there is a little mode here, right? So here, yeah. So yeah, basically our result has a better identity preservation than traditional non-reference based image. Non-reference based result, yeah. So well, this is preferred by our co-founder. I mean our result. Okay, lastly, so if we have multiple reference images, right? So we can do more things because a single reference does not provide enough information. Okay, if we have multiple references, why not use it? Yeah, so yeah, this is why Xiaomi used it in DMDNet. Okay, yeah. So well, Xiaomi's DMDNet is based on dictionary learning, and then our method is based on diffusion model. So so our method has two. Okay, so let's think about this problem. So this is like a personal. So we call it this is a personalized restoration problem, and this is also like a personalized generation problem, right? And then very close to the work is dream booth. Yeah, and then our method is like a dream booth, but specifically tuned to this problem. So our method is okay. First, do dream boost. Like we fine tune the stable diffusion. We personalize the stable diffusion, and then we adjust the encoder. Okay, to be adapted to this fine tuned stable personalized stable diffusion. Yeah. So we call it a dual pivot tuning. And then let's see a result. So this is the George Clooney. Yeah, this is the degraded input. This is the by traditional blender restoration. Well, this is not like, I don't think this looks like a George Clooney. And then this is our result. Okay. Well, so the method is not that trivial. So I just said, so we have this dual pivot tuning. But if we do some like a single tuning or some other combination, then the results will be worse than ours. So this is another result. This is very interesting. So you can clearly see that. So from the Tyson's face, right, the tattoos are preserved in our result, but not well preserved in other methods. So yeah, so this is just another example. So our quality is also better than previous method. Okay. Okay, so I just talked about the face image restoration methods, and then the next question is when should we apply enhancement? Okay, so well we should apply the enhancement when the face image quality is bad. Okay, but current method. So for these two images, right? This is a schedule. For these two images, the traditional method will say that okay, this method, so the left image has a higher quality, okay. But I think that our users will definitely think that the red image has a higher quality. Okay, so actually face image quality assessment is not a trivial problem. So current methods do not learn to separate the degradation from content. Okay, so this is the result of our result. So basically, we learn to extract the degradation We learn to extract the degradation information. Okay, so we extract the information and then project it onto this 2D visualization. So you can see that images with the same type of degradation are projected into the same cluster. For example, like lower resolution cluster is here, overexposure, yeah, here, like a motion blur is here. So what is our method? So traditional method will usually use a contrastive learning. So for each low quality image, so there is a label, like this is a motion blur, and then this is oversaturation. Then for the extracted features, so this tool should be similar, and then this tool should be very different. Yeah, but this method needs the labeling. Okay, so how about we do something smarter, right? So how about we solve the problem without this labeling? Yeah. So this is our result. So by the way, so this paper is going to be presented in CVPR this year. Yeah. So the basic idea is we can do this. So for our image, we can synthesize all type of degradations. Okay, and then so we have the degradation feature extractor, and then we can extract the representations, the degradation representation for each image, and then for each image, it can be represented by it can be projected or represented by linear combination of many real images. Okay, and then so this new proxy feature should be very close to the degradation representation of this one, and it should be different from this one. So if the degradation representation is extracted very well, then we should be able to see this. Yeah. So in this way, we do not need the labels. Okay, now so the face IQA problem has been fixed by the proposed method. Okay, so just look at this one. So the current method says it's bad, but our method says it's good. And then for this one, current method says it's bad, maybe because it looks more on the background, but you know, we should all focus on the face, and then our method fixes the problem. Okay, so face IQA can be used as the judge, like to whether to apply face image restriction or not. It can also be used to filter the data. So if you have a lot of face images, right, and then you can just easily filter them to do some like other tasks. Okay, so yeah, so this is just show one result. So we rank all the, so this is the faces are from the same person. So we just rank them based on their image quality. This is another person. So yeah, the higher quality is here, and then lower quality is here, is in the right bottom corner. Okay, I just talk about the face image quality assessment. Another interesting question is, okay, can we predict the quality of a shorter video Okay, so why are we going to do that? So imagine that a creator upload a video to our platform, right? Then how can we like promote this video? So okay, if this video has been watched by like 1,000 people, then based on the history, we can somehow know this video is popular or not. But this is a newly uploaded video. We have no way to know. We have no user engagement history. Okay, and then so in the industry, the usual way is okay to broadcast the videos to a small amount of people, and then decide whether we are going to recommend it based on this 40 people's reaction. Okay, well, okay, we know that. Okay, this so there are many problems about it. First one, so 40 people is a small amount, and if it's a better quality video, then this 40 people will not have a good experience. Okay, and then we think we as a researcher we think can we predict the engagement? Okay, can we predict whether this video is going to be popular later? Just by analyzing the video content itself. Okay. Well, we do not know whether we did not know whether we can do but yeah. So, but we have the data. Then we just tried. So yeah, the problem is just giving a video, predict whether it's going to be popular or not, or whether it's going to be interesting, whether it's interesting or not. So there are two problems that need to solve. So the first one is so we have a lot of data. So we have like 10,000 of videos, and then each video has many metrics. Okay, so in our database, so yeah, 10,000 videos, and then each video has the user engagement history, like a rate, okay, average watch time, the number of comments, etc. Okay, so first question is what metrics to learn? So can we predict this video's like rate? Okay, it turns out that it does not work in our platform. And then can we and then the left one, so can we predict each video's average watch time? Then actually the answer is no. So why? So here the horizontal axis is the video duration. So each dot is a video. Okay, each video has a video duration and its average watch time. Okay, so if the metric is the average watch time, then it's not a fair. So you know, longer videos have longer watch time. Shorter videos have a shorter average watch time. Okay, and then how about average watch percentage? So this is the average watch time divided by the video duration. This new metric is better, but still not a fair for all the videos. And then this is our method. So we firstly find that so for each video duration, okay, the top, so the longest average time will form a line. Okay, this is very interesting. We do not know why. Maybe we need someone in the sociology who can explain it. Yeah. By the way, so yeah, so this is a very linear. Okay, and then we consider that okay, for this group of videos. So this is the most interesting. This is the average time of the most interesting videos. Okay, and then we just divided each number by this most interesting videos average watch time, and then we get this curve. We call it a normalized average watch percentage. So now every video shorter or longer are in the same level. Then actually and then the learning is not going to be biased. Okay, And then the other one, so the other metric, engagement continuation rate. So what it is? It is the probability that this video is watched for longer than 5 seconds. Okay, so and then interestingly, for this metric, this long watch rate, it is quite flat. Okay, so then it means it's also a fair metric to learn. And then well, this normalize the average time and then the engagement, the long watch rate are kind of correlated. Okay, and then here are the two observations. Okay, for this engage for these two metrics. So basically, so for each of the two metrics, they follow this by model distribution. So there's a peak here and then another peak here. So why? So this is because this is due to the users behavior. So okay, I'm not sure whether you guys use the TikTok or Douyin. So I think okay, if so when you like a swipe in the short video platform, right? So usually either you watch a video for less than 5 seconds because you think that video is not interesting, or you watch the video for a longer time. That's why. So we have this bimodal distribution. Okay. And then the second question is what features to use for the prediction? Yeah, so what kind of features that we can extract from the videos that can help the prediction? Yeah, we tried like a VQA, quality feature. Okay, and well, quality feature itself already helps a lot. And then we also tried other features like a background sound, where we know that okay, background sound is also important. Many short videos are added like the very engaging music, and then also like a tile distribution, video captioning. Yeah, so well, some features doesn't help. Yeah, so and then this one, so this feature combination can achieve the best result. Okay, so lastly, our method can predict average watch time or normalize the average percentage with a very small RMSE very close to the ground truth, and then the long watch rate is also very close to the ground truth. So we can use it to recommend top videos. Okay, so let's see some results.
3 different ways to get on a skateboard. First up, we got the sledgehammer. Just chuck your board down, get it right under your toes, and hop on. This one looks pretty silly, but it's actually really fun to do.
Pause it. Yeah. So this video's duration is 22 seconds, and then it's ground truth engage. So long watch rate is 0.7, means 73% of the people watch this video for longer than 5 seconds. And then this is our prediction, very close to the ground truth. And then for normalize the average watch percentage. So people usually watch 81% of this video, and then our model predicts it's 84%. Okay. And then for this video, average watch time is 17 seconds. Okay. Okay. So this video is an interesting video. Okay, and then our model can predict that.
3 different ways.
Okay, this is another video.
Whoa, she's getting up there.
Wow.
Okay. Dang.
Don't hurt yourself. Don't hurt yourself.
Careful, young lady.
That was impressive, young girl.
Oh, yeah, okay, I'm going to pause it here.
Are you sure?
Well, you can find this video in our platform. Yeah, you can you can watch the full version of the video. Okay, and then so this video is long. Its duration is 24 seconds, and then yeah, you can see that for the two metrics, our prediction are very close to the ground truth. Yeah, and then our algorithm know that can predict that is a interesting video.
Whoa.
And then show another example. Yeah, so this is just someone to show the bag. Okay, well, I'm not sure. So maybe girls or females here feel that this video is interesting. I'm not sure. Yeah. Okay. So sorry, I shouldn't have this bias. Okay. Yeah. So this video is pretty long, 30 seconds. Okay, and then the long watch rate is just 11%. Okay, only 11% of people watch this video for longer than 5 seconds. And then our prediction is very similar. And then same for another metric. And then our algorithm say is an interesting video. Then this video is not going to be promoted. Okay. Okay, now let me talk about something about a QR code. QR code is very important because before we did this project, so this is a guideline. This is the guideline for all the people who use QR code to promote their stores. Okay, by the way, this is so in Snapchat we call it a snap code. This is another form of QR code. And then our company tell all the store owners that okay, you should print your QR code to be on a bigger paper. Okay, so suppose this is the 1x, and then if the user if the user is 7x away, then the QR code scanning is going to fail. So yeah, this is the before we did this project. Yeah, so let's see why. So when the camera to code distance becomes longer, you can see that the code's quality deteriorated, becomes worse. Okay, I think at this moment it's very hard to know whether there is a dot there. Okay, and then this is our now we have our new result. So this is the previous method. It already fails, but our method can still detect the two codes. Okay. Yeah, it's just successful, but it's going to be fail. It's going to fail. Let me switch to another slide. Okay, and then so this result show that okay, our algorithm is resilient to code as tilt angle. So you can see that okay, for the left one is already fails. So for our method it's just recently fail. Okay, and then the same method can also work for more common QR code. I'm going to skip this slide. Okay. So well, we did this project back in 2019. Okay, and then back then the traditional method is like do the square detection first, and then do the alignment, and then binarization, and then convert the binary image to the bits, and then this is our method. So we fine tune this QR code object detection network, and then we use a CNN to do this two tasks together, alignment and bits. Yeah, so it has been integrated into the app and used by millions of people every day. And then, well, at that time also, this is a big success. And then actually later we found out sometime later, so we were the first one to do it. And later, WeChat and Apple released this one maybe several years later. And then actually, so well, in the beginning, we didn't know whether this is possible or not. Yeah, and then but we still wanted to tackle this problem just because we did this theoretical analysis. How many pixels are needed for decoding our QR code? Okay, so maybe I can put it here. Imagine this like a 21 by 21 QR code. Okay, how many camera pixels are needed? So by next sampling, we might feel that if 21 by 21, then minimum should be 42 by 42, right? 42 by 42 camera pixels. But actually, it's a binary image, right? And the number of pixels could be less than that. Okay. Okay, maybe let's say okay. Just because it's a binary image, then we might only need like a 21 by 21 pixels. But can we go even further? Okay. Interestingly, this QR code has the redundancy in design, so you do not need to recover 100% of the bits. So based on the redundancy design, maybe you only need to decode like a 50% of the bits. Then you are still good. Then actually you can basically theoretically you can use less than 21 by 21 camera pixels. Okay. Yeah, and then we also have this lightweight network, so it should be very, very fast. Okay, after we did that project, then we say, can we even go more crazy? Okay, can we do further distance QR code scanning? And then, so this is the work that we did by Sizhuo. So the basic idea is, okay, so suppose you are in New York, okay? So you are here, you scan a QR code, okay? You actually your QR code has low resolution, but actually you do not need to compare your QR code to millions of codes. You only need to, so your candidates are just the codes nearby. So you only need to compare to maybe 100 codes. Well, our app should have this database of all the code at the location beforehand. Yeah. Okay. I'm going to skip this part. This is the video frame interpolation. It is also interesting work. And it also has been used. So this is the product UIs. And then we also did this so more interesting camera. So we did a selfie anti-distortion. So convert this selfie to this image. Okay. And then for AR glass, we did the co-design of hardware and software on like low light imaging with flash. Resource limited 3D sensing. So okay, so for active sensing, how can we use a minimum power but sense a very long distance? And then some fancy thing. Also, I'm going to post the slides on website. So okay, 3 fancy things. How can we detect transparent glass? Okay, and then how can we design a transparent display? Lastly, how can we design a transparent camera? Okay, so you can find the answers in my slides on website later. Okay, to summarize, it takes some time. Okay. Okay, to conclude, yeah. So, so our company have these 2 core products. One is the app. Okay, people use it to capture a lot of photos and then share them every day with their friends. And then the AR glass. So we have many. Then let me see. Let me try again. Okay. Okay. Maybe I can just mute. Okay. Yeah, so two core products. Okay, one is the app, with 400 million daily active users. Okay, and then the AR, the very fancy AR glass. Then we have many exciting and real computational photography and computational imaging problems. Yeah, and so maybe the last message that I want to convey is so our lab is great. So please encourage please apply for our lab as your internship place, or encourage your like lab mates to apply for the full-time job in our place. Yeah, thank you.
Thank you for Dr. Wang for amazing talk. And now it's the QA time. If you have any questions, please directly ask Dr. Wang here.
Do you want to? Yeah.
I have two problems. So first one is a reference-based face restoration. So I think there are many challenges in this task. For the first one, if the reference image have different pose or with or without sunglasses, which is different from the input LR image. So how do you have any design in your method to handle this problem?
Okay. Yeah, this is a quite a challenge. So actually for our single reference based method, we didn't solve it. So this method is based on cell gun. We found that this is the method limitation. But then for multiple reference based method based on diffusion model, with I did not do this test, but I feel that this new method is very powerful, and our code is ready. I think we can release the code very soon. I think this new method, dual pivot tuning for personalized researching, can solve the problem. Yeah.
Okay, thank you very much. And the second question is about the QR code super resolution. So so how do you prepare the training pairs, and do you add some recognition prior to train the model?
Recognition prior?
Yes.
What is
yes.
recognition prior?
The QR code recognition. So we constrain the recognition result like a bit.
Okay. So for this QR code scanning, right, project. So very important thing is how can we get the training data? So we actually synthesized all the data because we understand the degradation process. Okay, and then for the training pair, so the ground truth is the bits. Is the bits. Not it's like a 21 to 21 bits.
Thank you very much.
Yeah, thank you.
Thank you for the presentation. I have a very simple question actually. So because if my understanding is correct, your application is for the mobile.
Yes.
So like do all the algorithm running on a mobile, or you also like run some of them on the cloud? Like if it's on a mobile, do you have any like specific design like about the efficiency or something on your side, or it's like more from the product side? Yeah. Thanks.
Okay, yeah. Wow. Okay, this is a very good question. So first one, so for the algorithms that we designed, so I would say 70% are running on the mobile on the client, and then 30% are on the server. Okay. For example, the video engagement prediction one, so it is on the server, just because we want everything to be on the client, but sometimes if the model is pretty small, then the quality, I mean the results will not be that good. The performance is not going to be good. And then the second one, so so is the efficiency part solved by the product team or by us? I think for the computational photography, area, the very important thing is how can we design the algorithm on client or on edge device. I feel that we should not leave it to the product team. So we understand the algorithm, and then we just need to design the algorithm according to the mobile chips constraints. Yeah. So efficient image researching is a researcher's problem. Okay, yeah, thank you everyone.
Hello, everyone. Thank you for coming. So generally, I like to start my presentations by parsing my title a little bit, just so it appears a little bit more accessible, a little bit less scary, a little bit less intimidating. So passive here just refers to the fact that our imaging approach that I'm going to talk about is not synchronized to any of the light sources that are used to illuminate our scene. I'll discuss what ultra-wideband means in this context in the coming slides, and then I'll discuss single photon imaging, sort of a new exciting imaging modality. I'll discuss a little bit about how they work, what we can do with them, and then I'll discuss our approach. And I'd like to start by showing you this clip. It's called The Powers of 10, and it starts off by showing a scene that is a meter wide, and every few seconds it's going to zoom out so that the width increases by a factor of 10. So after a few seconds, you're going to start seeing the city of Chicago, and then the Great Lakes regions, and eventually you're going to be able to see the continent, the planet, the moon, the Earth's orbit, and then finally the entire solar system. So this is a huge amount of magnitude that has been covered. And so imagine a video camera that allows us to zoom in and zoom out over a similar range of magnitudes, but in the time domain. So it allows us to record phenomena taking place concurrently at all these different time scales and observe them later. And if you think about it, even within just 1 second of video, there's a whole solar system of time scales that we ought to be able to record simultaneously. And a video that can, and a camera that can do this would allow us to slow down or speed up a live video recording by a factor of billions, depending on what visual phenomena we like to observe. From fractions of a second to milliseconds, to fractions of microseconds, all the way down to picoseconds, where we can start seeing the propagation of light itself. And so what I really mean by ultra-wideband imaging is this ability to capture both ultra-fast and slow events simultaneously, as well as anything in between. And hopefully I'll convince you during the talk that this is not quite as easy a problem as it might look at a first glance. Right? Now, the reason we want to capture these ultra-wideband videos is because things happen at different speeds. And so it's crucial to have the capability to capture them simultaneously. Well, okay, so how close are we to being able to do this today? Well, let's start by talking about some modern off-the-shelf options for high-speed imaging. And if you've ever spent any time on YouTube like me, you might have come across this channel, the slow-mo guys. And basically, they've got this high-speed camera that they go around with, capturing videos of all kinds of different phenomena, from water droplets to lightning to speeding bullets. Okay. And that's great and all. You know, off-the-shelf cameras these days are getting faster and faster. And these days they can go all the way up to 1 million frames per second, which is already 6 orders of magnitude. And indeed, when we record with these devices, we can theoretically record them from any length of time we want. So we can capture events that take place over time spans of seconds, days, months, or even more. But as I said, we want to image at shorter timescales as well. And this regime is called ultra-fast imaging. But when we get to these short timescales, we have a simple problem, which is that we need a lot of light. And not just a lot of light. In fact, ultra-fast imaging today requires precise synchronization with a single dedicated high-speed light. And the reason for this can be traced back to Doug Edgerton, the father of high-speed photography.
And that's because all imaging techniques that support frame durations shorter than a microsecond still fundamentally rest on the principles he laid out 80 years ago. Now, before I talk about ultra-fast imaging, I want to play this ad from Gatorade that provides some clues into why we need all these different components. And before I play this clip, I just want to emphasize that there's no special effects here. There's no post-processing done. So what you see being played is going to be exactly what you would see if you were there in the room yourself. I'm going to drink some Gatorade while this plays. So basically, they were able to animate raindrops in the form of people moving. And how did they do this? Well, obviously, they were not moving raindrops from frame to frame. And so I'll show you a different clip that hopefully reveals the magic behind this. Right? So first, you've got a few things happening right now. You have this array of Gatorade bottles, which is releasing water in a very precise and controlled manner. Then you've got this fast-moving event of the water dropping due to gravity. And finally, you've got these lights that are flashing very fast to take a brief snapshot of the moment these water droplets align in the shape of a human. And all of these are synchronized together to provide this illusion of water droplets moving as a human running. And in fact, this idea of synchronizing events with brief snapshots was taken to an extreme by Velton and Raskar 10 years ago, where for the first time ever, seeing light propagation through everyday scenes was made possible. And here you can see his iconic video of a laser pulse moving through a bottle of Coke. So how is this done? Well, let's think about why we need each of these different components for ultra-fast imaging, starting with why we need a dedicated high-speed light. And remember this egg video I showed you guys earlier? Well, here are the slow-mo guys again, preparing to capture that video. And the interesting thing here in this photograph is not just the fact that they've got this really fancy camera, but also the fact that they're clearly shooting in the blazing sun. And so if you need these kinds of conditions to shoot a good video at the microsecond timescales, then there's absolutely no way natural light is going to be able to allow you to shoot a good video at timescales 1,000 or 1,000,000 times faster, because you would need natural light to be that much brighter, right? And here I have a video of Doc Edgerton himself demonstrating why a source that is not only bright but super fast becomes critical here. Right? Hopefully the sound plays.
Still photographers are very busy these days snapping pictures of fast-moving objects and whatnot. A fair degree of clarity is attained with the aid of the modern flash bulb attached to the camera. We'll see the results of this later. Edgerton uses the same camera. When it's hooked up to his things and stuff, however, he makes the average action picture look like a broken-down tintype. The high-speed light does it. Each flash of that light lasts 1/30,000th of a second, which is faster than a goose in a high wind. So, we take the picture. Here's that first picture made with the usual flash bulb. Note how the shoe and ball are blurred. And here's the photo by Edgerton, clear as a California morning. Well, some California morning.
So the record holder in high-speed imaging today, in fact, uses a variant of this technique, but with a very fast and very bright flash. And the fine print here is that they basically pack within a single laser pulse the energy of 1 billion laser pointers. Now, this is so bright that you most certainly would not want to have your hands or your eyes anywhere near that pulse, and you certainly wouldn't want to repeat it too many times. And so this imposes a major restriction on the time span of events that can be recorded. Alternatively, if you had precise synchronization with a light source, then we may not need a lot of light. And again, I'll let Doc demonstrate this for me yet again.
The principle of this high-class gadget is a light that flashes on and off at variable speeds. Through this invention, you can examine machinery in motion. Here, a common electric fan is used in a simple demonstration that even I can understand. Or can I? Anyway, when you direct this light on a fan and synchronize the light flashes to the revolutions of the fan, the blades appear to be stationary.
Right, so once we have frozen the scene in time, we can simply collect light for however long we want. Right, and again, the same idea was used by the video of the light propagation I showed you earlier. And though some of you may think that this is a moment in time being captured, in fact, it's actually millions of identical moments acquired over time spans of many hours using a pulsed laser that was synchronized with their camera. And the light here would actually be weak enough for you to put, say, your hand in front of the Coke bottle without any fear, but you wouldn't see your hand at all because it would be completely blurred out. And in fact, again, the fine print here is that you can almost never image any events occurring over time spans longer than the period between individual flashes. So recording is limited to less than a few nanoseconds. And so although this technique can image at short time scales that we want, it's limited to very short events. And again, finally, it's very important that we have a single light source in the scene. And again, I'll play a video to demonstrate why that's the case.
Anyway, when you direct this light on a fan and synchronize the light flashes to the revolutions of the fan, the blades appear to be stationary. To make sure they aren't, it's better to turn an ordinary light on the fan than to stick a finger into it.
Right, so in this case, if you had any sort of asynchronous light in the scene, it would just corrupt what we actually want to acquire. So we have a lot of techniques for ultra-fast imaging nowadays. But if we put all of these techniques in ultra-fast imaging on the same axis, we can make sort of a very simple observation, which is that they can only image extremely short events. But as I said, we're not interested in capturing only fast events. We'd like to be able to capture slow events as well as everything in between. So how do we image across 12 orders of magnitude simultaneously? Well, that's where single photon imaging comes into play. And before I talk about that a little bit more, I'm just going to sort of veer off and talk about imaging for a little bit. We're not going to go there yet. One common analogy to describe how a camera pixel works is through the use of a water bucket collecting raindrops, much like pixels collect charge generated from photons. And through the use of this water bucket analogy, I'll try and motivate the utility of being able to detect single photons. Okay, so imagine I have some neighbor, let's call him Bob. And one day Bob decides to put a water bucket outside his house before he goes to sleep. Now, when he goes to sleep, it rains overnight. So the next day he's gonna wake up and find his bucket filled with water. Now, I, being the friendly neighbor that I am, might decide to ask Bob, what happened last night, okay? And, he takes a look at the water bucket and then he can reasonably deduce that, oh, it must have rained last night because my water bucket filled up. And, if he wanted to go one step further, he might even go out and measure the water bucket level, and maybe he'll come back and say, on average, the average rainfall was 12.5 millimeters. But if you think about it, in my opinion, that's a little bit unsatisfactory because even though you know that it rained last night, there's a lot of missing detail, right? For example, there are questions like, when did it start raining? When did it stop raining? Was the rainfall a steady downpour or were there flash floods? And finally, was it even rain? That I might want to ask. And even though this at a first glance appears to be a sort of artificial set of questions, we can project them to what they would mean in a context of a camera, right? The first question is simply asking about, when did the lights turn on during the acquisition? The second one is about whether or not when the lights turned off. The third question about the steady downpour amounts to asking whether or not the photon flux incident to the pixel was constant over the acquisition time or whether it varied over time. And finally, the last question sort of posits whether or not there are other light sources present in the scene. And so Bob's a smart man. So the next day, instead of sleeping, he goes out and decides to goes out every 30 minutes and he measures the water level in each bucket. And he this time he comes back to me with a graph that may look like this. And even though he's only measured the water bucket level very sparsely, there's a lot more information we can learn here, right? So for example, you can see that around this time, because the water bucket level stayed constant, there was no rainfall at all. And around this period, you can tell that there was rainfall because the water level rised. And based on the slope of the curves, you can tell that the rainfall in the first one was heavier than the second rainfall. And finally, maybe right before 7 a.m., there's an uncharacteristic sharp rise, which might mean that someone had filled it up, tempered with your water bucket. So hopefully you can see that even with sort of like the simple curve, this rain level curve, gives us a lot more information about what happened overnight than the first case. Now we can take this example to an extreme. So suppose he's still unhappy and that Bob just happens to be this rich billionaire. So he goes out and gets this supercomputer and water bucket that has this incredible level of processing and ability to measure the water levels, so much so that he could time with high precision when a raindrop falls into the bucket. Okay, so in this case, he would have so much information. He could completely recap the entire history of what happened overnight. And that's very different from the first case I described, where he only knows the outcome of the events overnight, and therefore effectively has no idea about the history of what happened. And similarly, just like being able to detect each raindrop gives us a lot of information, similarly, photons themselves are also rich with information. And this is where single photon imaging comes into play. So let me explain this in a little bit more concrete terms. Imagine the scene of a person, let's call her Carrie, moving around in a room. And we can take a look at this pixel on this chair. Now, the light intensity at this pixel is going to look like some curve like this. So every time she covers that chair, it's going to drop, right? And now radiometry tells us that basically the light intensity is a function of continuous time. And if we could observe this light intensity directly, then we could simply sample it for however many frame rates we want, from kilohertz all the way up to billions of FPS. Now, the issue here is that this curve isn't directly observable because light propagates as photons. But fortunately for us, as I said, these photons do contain the information we need to infer the light intensity over time. So rather than light rays looking like this as we imagine them, it looks a little bit more like this, where light propagates in discrete packets called photons, whose arrival in the camera is completely stochastic. And the key insight, though, here is that even though the arrival rate is stochastic, there's still a lot of information about the light intensity. So for example, if I were to turn on a bright source, that would simply mean that the photons arrive more closely spaced in time. If the source itself fluctuated, then the rate of photon arrivals will fluctuate as well. And you see this clustering effect happening because brighter intensity means more photons and dimmer intensities means less, hence the clustering. And finally, you may even have a case where you have a very dim light source fluctuating very quickly, so that photons arrive at a rate much slower than the light source's fluctuations, in which case you do not see this clustering effect. And this is the case where all techniques for ultrafast imaging will fail because they do not have enough light, enough photons to collect without the use of synchronization. Now, of course, in general scenes, we get photons from many different light sources, all operating at different speeds and different intensities, or from moving phenomena in the scene. And in this case, there's no way we can synchronize to any single light source. And this is the regime we call ultra-wideband imaging that we're considering. And here, all the information one can expect to know about light is the time of each individual photon arrival as provided by the photon stream. And the problem then becomes to recover the continuous light intensity, or in more formal terms, the flux that is incident at a pixel, given this discrete set of photon arrival times, right? So how can we take this discrete set of observations and recover a continuous time flux from them? Well, the key here lies in counting with photons, okay? And again, before I segue into this, I'd like to talk about counting briefly. So counting is something that's very basic that hopefully all of us know how to do. It's something we learn even as early as the age of 2 to 4. And my goal for the next 2 minutes is to try and convince you that counting is in fact no trivial matter. So let's suppose I've got these fruits in front of me, and I were to assign a value of 1 to each of them, okay? And if I sum this, I would get the number 4, which is simply how many fruits in front of me. I just counted. But there's no particular reason I need to assign the value of 1 to each fruit. I could have easily, say, assigned the following numbers instead. And in this case, if I sum them, I would get this number 13.6. Now, does anyone want to take a guess what 13.6 could mean? You're close. So in this case, instead of assigning 1 to them, actually, I'll add a symbol in front of them to help. Okay, so this is the prices I Googled, right? So if I were to assign them their price and sum this, then I effectively am counting the, the cost of the fruits. This is the second example. If I were to assign them these numbers instead, where the apple and the oranges have the same value, I end up with 24.6, that would be their weight, right? So depending on how you assign your value according to sort of this counting function, if you will, you can really think of counting as a way of measuring quantities, right? So in the first case, when my counting function, say, is 1, what I'm measuring is the number of items. In the second case, when this function is the price, what I'm measuring is the total cost. And finally, if I'm sort of if the function is the weight of each item, then I've measured the total photons. And similarly, we can do the same trick with photons, where we can think of counting with them as measuring with them. And even though we're not going to be measuring the cost or the weight of photons, there's still quite a few interesting things we can measure, which I'll talk about now. So I'll start, I guess this is the part where it gets slightly technical, but anyways, I'll start by introducing a process called N of T. And in fact, this N of T is called the counting process, and hopefully you'll see why in a second. So let me tell you how N of T is defined. So every time a photon arrives, we're going to increment it by 1. That's all. Okay. Now, the thing here is that N of T is actually defined over the continuous time domain. So I can query it at any point that I want, not just at the discrete set of timestamp arrivals. So if you can see my mouse, I could query it at, say, this point here or this point. Okay. And so there's a very natural question, which is, what does N of T measure? Right? In this case, it's very simple. N of T is just measuring the number of detected photons you get in some acquisition time. And sort of to be more precise, sort of this counting process is equal to the flux integral, which tells us how many photons we expect to detect, and some noise, okay? And I'll sort of visualize that here on this plot. So in solid, I'll plot the flux integral, which is the expected number of photon counts. And in dashed, it's the counting process. And the discrepancy between is this noise term I was talking about. And I'd like to just focus your attention on sort of this area. So you can see that as photons arrive, this counting process, if you will, is just strictly is just increasing over time. And so as more and more photons arrive, they become closer together. Now, as I said, there's no particular reason we need to go up by 1. So I could define a different process that I call NP of T, where I'm going to count using some proxy function, P, that we'll call the probing function. So every time a photon arrives, I'm going to increment this process by the value of P at that time of arrival. Now, because P is a function, it can be negative, and so this counter can decrease as well. Okay. And so now there's a question, what does this process measure? Because it's definitely not the number of photons that are detected, but there's a question of whether or not it's interesting or even meaningful, right? So the way it's defined is I'm just going to evaluate at P of T1, then I'm going to send P of T2, and so on and so forth, right? Well, it turns out that this sort of unintuitive way of counting, if you will, measures something that's very well known to us from linear algebra and very powerful. And that is, it's basically measuring the inner product of the function we use, the probing function, and the unknown flux we care about. Okay. And because this is the case, this gives us a, so this is the main idea behind our flux probing theory. And we formalized this concept where we define the sum of the function at the timestamps as the probing measurements, and formally we can say that they're equal to the inner product of the function up to some martingale noise. And you can think of the martingale noise as some stochastic process version of zero mean noise. And in our paper, we also showed that the probing measurements are approximately normally distributed with analytical expression for both the mean and the variance. And I'll talk about how we can use this for flux reconstruction. So suppose I've got the following set of timestamps, and at the top, I've also shown what the flux will look like. So it's the sum of 3 cosines, if you will. And I, for some reason, decide to choose my probing function to be cosine 2 pi of t, okay? And it's not really important what this function is, but all that matters is the fact that 1 hertz is a frequency that's not in the flux that we care about. So if we were to count using this function, and I want you to focus your attention here, you'll notice that what happens is that this process is going to go down at times, it's going to go up at times. Unlike the first case, it's pretty random what happens. Yeah, and over time, as more and more photons arrive, you don't get any sort of distinct structure from the process here, right? And that makes sense because, as I said, you know, what's being measured here is the inner product plus some noise, but because this frequency is not in our flux, there's no signal. So what you should see is strictly noise, right? So let's look at a very different case where now I'm going to choose my function to be cos 4 pi of t, and you'll notice that this frequency is in fact in our flux, right? And what you also notice is that, as I said, this measuring process can go down, okay? And I want to focus your attention here, right? So you can see that even though sometimes it goes down, for the most part, it's increasing. And so what happens is that, you know, when the frequency is in the flux, we get a very different structure in sort of this curve than when it's not. And so this gives us a very simple way to figure out what the flux is, namely that we start with the detected timestamps over time. And then we can select some orthogonal basis of functions. So in this case, we use the Fourier basis functions, and we're going to basically probe using each function to give us a noisy estimate of the Fourier transform of the flux. And now, because we know the distribution, we can easily come up with a detection threshold that allows us to distinguish which frequencies are signal and which are noise. And then as we get more photons, this detection threshold is going to get better and better. And then by simply applying an inverse Fourier transform using only the frequencies above the bound, we can reconstruct the flux. Okay. And now that we have this continuous time representation, as I said, we can sample it at whatever rates we want, from 30 frames per second to kiloframes per second, all the way up to billion frames per second. Now, there's a very natural question to ask here, which is that what is the maximum frequency we can recover? Okay. And I'm sure most of you who are familiar with signal processing has seen some graphic of this form. It's effectively a visual proof of the Nyquist-Shannon sampling theorem. And so for those of you who aren't familiar, let me just quickly explain. Suppose I give you a set of points, and I want to know what function sort of define these points. Then in this case, there's a few candidates. Even though my real function looks like this dash one also looks like a possible candidate. And that's because I basically undersampled the signal that I want. And the theorem effectively states that the maximum frequency of a signal without aliasing is half the sampling rate that you have. Okay. But there's a question of like, what is the sampling rate of a photon stream? Because as I said, these photons arrive stochastically, so you don't have regular sampling. And one natural candidate might be the average photon counts per second. So on average, how many photons are you getting? In fact, this is what we had thought initially, but it turns out to be wrong, and here's why. So it turns out that the theorem only applies to a case of regular sampling. But if you had an average sampling rate, then because you have stochastic sampling locations, then the maximum frequency may be much higher. So here's an example. You know, suppose I randomly select these points to query for the function I care about. Even though I'm using the same set of points as before, I can disambiguate this curve from this one. And effectively, in our paper, we showed that what matters in our case for the maximum recoverable frequency is not so much how many photons we detect, but rather how precisely we can time them. And in fact, there's also a really cool paper from Science from the 80s that discusses this notion of irregular noisy sampling, but for spatial frequencies instead. And they basically show that the quasi-random spatial arrangements of our photoreceptors effectively turn high-frequency signal into white noise rather than aliasing them as low-frequency signal. And so this is what allows us to sort of image across 12 orders of magnitude simultaneously. And let's look at some of the cool things now that we can do this, right? So you can think of ultra-wideband imaging as a microscope for time. And let me give you an example of what I mean. Beginning with an experimental setup shown here, we've got what's called a single pixel SPAD. So a SPAD is just a sensor that will detect these photons. This SPAD observes a single point on this box. And that point receives light from both a ceiling bulb, a pulse laser that has already been diffused, another laser that operates asynchronously from the first, and finally a laser projector playing a video on a diffuser. And the way the laser projector works is by raster scanning or sweeping an image plane, sweeping a laser beam across an image plane very quickly. And our pixel just collects all the photons from all these light sources without any idea about where the light comes from. And just to show you what the front looks like, this is the pixel we'd be looking at. So you can't even see what the video being played is. So after reconstructing the flux, we can visualize how it varies across time scales, in this case, spanning roughly 9 orders of magnitude. So in the scale of 1 second, we can see the roughly 60 Hertz refresh rate of the laser projector. Over tens of milliseconds, we can see the roughly 900 Hertz flicker of the light bulb. Zooming in even further reveals the time-varying modulation of the laser projector. At the scale of microseconds, we begin to see the 3 megahertz laser. Zooming in even further, we can start seeing both lasers and their relative peak amplitudes. And finally, at the nanosecond scale, we can resolve an individual laser pulse. Now, remember how I said the laser projector was playing a video? Well, here's what that video looked like. So our method also enables a type of non-line of sight imaging where we can recover the video shown by the laser projector from our observations of the diffuse raster scan signal. And in fact, more recently, we've made some improvements to our method, so we're able to now recover a 5-second sequence using the exact same set of data, and I've added sound for fun. Now we can extend this idea to 2D and capture videos of ultra-wideband scenes as well. So let's go back to the video I showed. Got a fan spinning that's illuminated by a laser pulse. Now, by rendering the video at hertz to kilohertz rates, we can see the motion of the fan. And as we push to megahertz rates, we begin to see pulses of light from the laser. And approaching terahertz rates, we can visualize a propagating wavefront and the fan blades frozen in time. Now, this is far more powerful than conventional active transient imaging, which blurs the fan blades because they move at a much longer time scale than a pulsed illumination. And finally, because we can reconstruct the flux, we can also sample it however we want. So we can create all sorts of new visualizations that were simply not possible before. So just to recap, here's what a normal transient video with the fan blades frozen in time look like. Okay. Here's what that looks like if we decide to freeze the laser pulse. And finally, we can also have both of them moving simultaneously. Now, I started this section by talking about our goal, which was to be able to image across 12 orders of magnitude. We haven't quite achieved that yet because our device timing resolution has about 16 picosecond jitter, which only allows us to cover 10 orders of magnitude. Furthermore, our dead time limits the minimum event duration we might have. That being said, as technology advances, we expect this gap to be bridged, and this is perhaps something that is either resolved through new devices or through computational means. Looking ahead, our method gives us this incredible ability to asynchronously reconstruct flux. So we may be able to start harvesting photons emitted from other light sources for various applications such as 3D reconstruction. And if we can do this, we may also want these devices to be able to perform these things in real time. So we need tools for being able to do ultra wideband imaging in real time. Another application may be scientific imaging, such as astronomy, for something like detecting fast radio bursts, where we have absolutely no idea when these will happen. So we need to observe the sky for long stretches of time on end, and then be able to zoom in and pinpoint when a radio burst happened. On the microscopic end, there's protein folding that occurs on the order of microseconds, and it'd be nice to be able to zoom in and observe that behind a microscope, of course. But to be able to enable these applications, there are a lot of challenges we need to overcome in signal processing, the most critical of which is efficient processing of photon streams given that even a normal scene consists of millions of photons per second per pixel. So the amount of data we collect is vast, and we need new algorithms to process all of these information smarter and faster. And we also need new ways to store this huge amount of information. And currently in the paper, we focused on processing the photon streams for each pixels independently, but with sort of emerging 2D sensors, we also need new theories to model the spatial temporal distribution of these photon streams that will not only enable efficient processing, but also may provide additional information such as correlations between pixels. And finally, there's a question of how do we even visualize or render these ultra-wideband signals with so much significant variations in both the intensity, but also in the time domain. Now, these devices are not just some theoretical device that may come in the future. They're here already, and companies are actively investing in single photon cameras such as Canon, as well as Apple, where the LiDAR scanner is in fact a SPAD. And finally, I sort of want to end this talk with this nice video from NASA. So NASA has this space mission called Psyche. And one of the things they're testing is a sophisticated new laser communication technology that encodes data in photons to communicate between a deep space probe and Earth. And the hope here is that by using light instead of radio, they can communicate more data in a given amount of time. And so recently they were able to transmit this video of taters over 19 million miles, or I guess like 30 million kilometers. Now, the sensing device that enables this communication technology are in fact single photon devices that I talked about today. So the techniques that I've discussed may be amenable to this as well. Now, of course, I have to acknowledge my wonderful collaborators without whom this project would have just not happened. And finally, links to the project on my website are here. Thank you. Great. Huh? Or we can go for lunch. Okay.
How long the data set to generate?
Okay. Oh, it ended up in like a couple hundred. So the problem is not just the data we capture, but then so we have like let's say 100 by 100 of photons. So that's 10,000 photons. So then 100 by 100, 100,000, like a billion photons, a billion like timestamps we get. But then we need to like process these timestamps, and we have to probe up to like the gigahertz. So we have like, in our case, we have like probably 1 to 10 billion frequencies that we're checking to figure out like, is there signal or not?
In terms of time, how long?
Oh, now it would take, so for that 1D example, it took like 2 hours to process everything. Yeah. For the video, we have to play some tricks.
But the whole data set like giga or terabyte?
It would be giga, like high, like more than 10, probably somewhere between like 10 to 100 gigabytes. Yeah. Well.
Fantastic pattern of photon arrivals. Are you thinking about the distribution of wavelengths?
Not so much here, because what ends up happening is you just have photon, or you have like the Poisson process that dictates the arrival of photons, and that's determined by like the light intensity curve, and I think all the wavelengths that cobbled together, right? So you're not gonna be able to separate color depending on their arrival. Yeah, but if different lights were flickering, so you have like a flickering red source and a flickering blue source, and they flickered at different rates, then you could disambiguate that without needing a bare pattern. Yeah.
By the way, do you have actually the 2-hour collection for each pixel? What kind of SNR should achieve to construct that?
In this case, for the video, we probably were using about 10,000 photons for each pixel. So if you think about like a normal camera, the full wall capacity is around like 20,000 to 40,000. So within like a 30 FPS. So I think we're getting like less photons than you would need for like a normal camera, like a normal camera image.
Yes, in terms of photon, the sound noise is only the SNR 100, but you have the
so
device noise.
There's quantization noise like jitter. So you have a timing precision of 16 picoseconds, but there's no read noise in this case. There's no read noise. So sort of the traditional metrics of like what would the SNR be, it's not as like, it's not directly mappable to what you'd get in an image. You always have shot noise. If you have like 10,000, yeah. Turns out that, so there's two canonical like stochastic processes. One is Brownian motion. The other one is the one you get from Poisson process. So this is the one you get from the Poisson process. So it's not Brownian motion. Sorry, I can't hear very well.
So like you guys have like a process, which is discrete counting, and
Mhm.
then you have a something times that
Like the integral?
yeah. So
Yeah.
what is that like term? Like what like the martingale?
The martingale. It's the difference. I guess it's effectively the difference between the process you get and what it's supposed to be, like the integral of the flux. And so that one is, it's effectively the noise you get from a Poisson process if you subtracted the expected counts. Yeah.
One more question. And I noticed that there is a spectral selection module and
Spectral selection module.
yeah, it's just a spectrum decomposition.
Oh no, we captured like the RGB separately and then combined them.
So I'm not sure that if it can work on the continuous spectral,
You're
such as sunlight or incandescent light.
I don't think I followed the question. Could you?
Since I noticed that it's the passive things or function matching,
Mhm.
and I think it's more like in the lab environment, but I want to know if it can work on the more general environment, such as which consider the multiple reflection or the continuous natural light.
Right. So what we're doing is all you get are the photons.
Yeah.
So what the camera sees effectively are photons.
Yeah.
It doesn't know where this comes from.
Yeah.
Right now, what we're doing here is just trying to reconstruct the flux at the moment. So we're not making any assumptions about how that flux was generated, whether there are multiple bounces that seen, whether or not it was sunlight. Right. What sunlight would affect is how many photons you do get, and that sort of there's like sort of an electrical reset called dead time. So if you have a lot of sunlight, then you're not going to detect all of the photons because the sensor takes time to reset to detect it. But you would still be able to reconstruct flux for like a sunlight, but it would probably just be a constant flux.
Yeah.
Like there's no sort of pulses being sent. But this sort of fluctuation is not related to like the spectral content. So it's the like brightness variations over time, not the color spectrum. That depends on how you decide to analyze the flux that you get back at the end, right? But whether or not we're not making any sort of assumptions about what is happening in the scene to reconstruct the flux. So sort of being able to estimate material properties of things from that flux is sort of like would be like a more downstream application. And you probably want to analyze like how does the flux variation change over time and analyze that versus just, in our case, in this work, we're just trying to reconstruct it. So it's raster scanning. So like you can think of a video as like a 3D volume, but because it's raster scanning and we've got our diffuser, that 3D volume gets mapped into a 1D signal. And so we just take that 1D signal and like remap it back into 3D. Since we know like it's height and resolution, and there's sort of some timing information we need, like when this first pixel is, that we kind of estimate from the scene. But you basically take this 1D signal, and then you remap it into 3D and get a video back. All right, that's everything.
Yeah, it's 3 megahertz and 40 megahertz. So when you actually listen to the frequency, you have to select it, or
sorry, what?
You have a 3 megahertz pauser, right?
Yeah.
Pause leader, 3 mega and 40 mega.
Yeah.
So this is carefully selected?
No, we just chose, we chose them so that they're not too close. Like we wouldn't want 3 and 6 megahertz, but then the 6 megahertz, you wouldn't be able to tell the 6 megahertz because the high order 6 megahertz is in the high order of 3 megahertz, right? So it chose 3 and 40 to be roughly co-prime, but you can make like you can choose like you choose 2 random frequencies that you should still be able to discern.
Do you have a paper on this one?
No, there's a paper that's it's on there. It's ICCV2023.
Okay, thank you.
I actually have a question about the
Okay, you work with event cameras.
Yeah.
I know someone who wants to talk because he